What if one day, the universe just stopped expanding? Imagine it. One instant, space itself is stretching, galaxies drifting apart, light from distant stars stretching into red as it crosses an ever-growing gulf, and the next instant, nothing. No more growth, no more widening emptiness, no more cosmic stretching. The great silent balloon of the cosmos holds its breath. What would you see? What would you feel? Would we even notice right away? Or would it take millennia before the signs began to reveal themselves? But before we continue, subscribe to the channel so you don't miss out on any of these videos. Picture the night sky you know now. Those twinkling stars, those faint smudges of far-off galaxies, each one is part of an invisible ballet, a slow-motion expansion that's been going on for nearly 14 billion years. The stage is enormous, the actors countless, the movement relentless. And then, an impossible moment. The movement stops. There is a deep and eerie stillness in the idea. A universe in motion is something we take for granted. After all, it's not just stars that move. The very fabric of reality is expanding underneath them. Without it, we're left with a cosmic standstill. It's like imagining a raging ocean that suddenly becomes a frozen plain of glassy ice, every wave held in place, every current locked. It's a question that forces us to confront the limits of our understanding. What happens when the engine that drives all large-scale cosmic change simply shuts down? Would the great structures of the universe begin to drift back toward each other, pulled by gravity's ancient grasp? Would light from distant galaxies arrive frozen in its Doppler shift, painting the sky in a way no one in history has ever seen? Or, and perhaps most chillingly, would the absence of expansion set the stage for something catastrophic? A reversal of everything we know? This isn't just idle curiosity. The expansion of the universe is not some background detail in cosmology. It is the backdrop against which every story in the cosmos plays out. It shapes the birth of galaxies, the cooling of space, the destiny of stars, and the very possibility of life. Stopping it would be more than pressing pause on cosmic history. It would be rewriting the ending of the universe's story altogether. The sheer mystery of this thought experiment is intoxicating. Scientists don't just study how the universe began, they also obsess over how it will end. Heat death, big crunch, big rip, these scenarios all depend on what expansion does. But in this case, we're imagining something even stranger: no final acceleration to infinity, no violent collapse, at least not immediately. Just a still universe. The kind of thing that seems simple when you say it out loud, but whose implications twist into a labyrinth of unexpected consequences. And here's where it gets truly strange. The moment you say, the universe stops expanding, you're not talking about a thing that's out there, like a planet or a star. You're talking about the thing that contains everything else. You're talking about space itself deciding to stop growing. It's not a matter of the stuff slowing down. It's the arena of reality putting on the brakes. And if that's true, what does it even mean for time, for motion, for the laws of physics that were written into the very bones of space-time at the Big Bang? This is the kind of question that doesn't just tug at the imagination, it yanks it into uncharted territory. It's the sort of thing that makes scientists both excited and deeply uncomfortable, because even if we can imagine the mathematics of it, imagining the experience of it is like trying to picture a color that's never existed before. So let's lean into it. Let's pull at the threads. Let's see what happens when the grandest motion we know, the expansion of all space, comes to a halt. In the moments ahead, we'll explore the physics, the consequences, and the wild possibilities of such an event. But for now, I'll leave you with the image of that frozen sky, that suspended universe. A cosmic stage, vast beyond comprehension, and suddenly, perfectly still. To understand what it would mean for the universe to stop expanding, we first have to appreciate just how long, and how steadily, it's been doing exactly the opposite. For the past 13.8 billion years, space has been stretching, pulling galaxies away from one another on the largest scales. This expansion isn't some obscure scientific theory, it's a measurable fact, first detected in the 1920s by Edwin Hubble, who noticed that light from distant galaxies was consistently shifted toward the red end of the spectrum. That redshift, wasn't because the galaxies were moving through space like a car driving down a road. It was because space itself was expanding, carrying them farther away like dots on an inflating balloon. In the early universe, this expansion was fast, unimaginably fast. Right after the Big Bang, there was a brief period called cosmic inflation, when the universe ballooned from subatomic size to macroscopic dimensions in a fraction of a second. After inflation ended, expansion slowed but never stopped. For billions of years, gravity, the great cosmic gatherer, tried to slow the pace. For a long time, it seemed possible that gravity might eventually win, pulling everything back together. But then came the twist, the discovery that changed cosmology forever. In 1998, two independent teams of astronomers studying distant supernovae discovered something shocking. The expansion of the universe isn't slowing down, it's speeding up. It's as if the cosmic car was coasting to a stop, and then, suddenly, some invisible foot slammed on the accelerator. This mysterious driver we call dark energy now accounts for about 68% of the total energy content of the universe. This acceleration is why the idea of a stop is so intriguing and so strange. Right now, the vast majority of galaxies are racing away from us faster and faster. Over time, they'll cross a point beyond which their light will never reach us. The universe is literally stretching itself into greater and greater isolation. To halt that process would be like reversing the tide of a cosmic ocean, an act so dramatic it would rewrite the laws of the cosmos as we know them. And let's not forget scale. Even at its current accelerating rate, this expansion is invisible to us in daily life. The space between you and your coffee cup isn't growing. Expansion only matters across billions of light years, where its cumulative effect becomes enormous. Galaxies a few million light years apart barely notice it. Galaxies billions of light years apart are being flung away at speeds approaching, and in some cases exceeding, the speed of light. For 13.8 billion years, this has been the rhythm of the cosmos, an unstoppable stretching, baked into the very geometry of space-time. Everything, from the patterns of the cosmic microwave background to the fate of the most distant galaxies, has been shaped by it. When we talk about stopping expansion, we're not just talking about changing the speed of things moving apart. We're talking about breaking a pattern that's been woven into reality since the very first fraction of a second after the Big Bang. And here's where it gets even more compelling. Because expansion is accelerating, not slowing, the only way it could stop is if something fundamental in the universe's underlying physics changed. Not just a little, but drastically. That's why imagining it is so mind-bending. We're picturing a universe that has spent its entire existence in motion suddenly deciding to do something it's never done before. Picture the universe as we know it, a vast, ever-stretching tapestry of galaxies, clusters, and superclusters, each thread pulled gently outward by the quiet force of cosmic expansion. Now imagine that motion simply stops. No gradual slowdown, no drawn-out fade. One moment, the cosmic fabric is stretching. The next, it's still. This is the essence of the big pause. It's not the violent crunch of a collapsing universe, nor the infinite drift of an ever-expanding one. It's a sudden, unnatural quiet on the grandest stage of all. On a cosmic scale, nothing like it has ever happened before. The laws of the universe, or at least the ones we think we understand, have been playing a continuous symphony for billions of years, with expansion as their constant rhythm. The big pause is that rhythm breaking. If we could somehow watch it happen, the first moments after the pause would look deceptively normal. Galaxies would still be moving through space as they always have due to their own local motions. Stars would still orbit the centers of their galaxies. Planets would still circle their suns. But the invisible backdrop, the stretching of the space between distant galaxies, would vanish. The silent tide that has carried everything apart for almost 14 billion years would be gone. It's like walking into a room where a fan has been humming for hours, so long that you've forgotten it's there, and then someone switches it off. The sudden absence of that hum is jarring, even though nothing else seems to have changed. The big pause would be that kind of absence, but on the scale of the entire cosmos. And here's where it becomes more than just a curiosity. Expansion isn't just a side effect of the Big Bang. it is a defining condition of the universe's behavior. It determines how light travels, how structures form, how temperatures change over cosmic time. Without it, everything downstream begins to shift. The distances between galaxy clusters, the temperature of the cosmic microwave background, even the ultimate fate of matter itself would take a new and unfamiliar path. A paused universe would also carry an unsettling implication. If expansion can stop, it means something has fundamentally changed in the balance of cosmic forces. It would signal a shift in the dominance of dark energy, gravity, or perhaps something stranger that we haven't yet discovered. And whatever caused it to stop might not be finished. It might push the universe toward an entirely different destiny, whether that's a frozen eternity, a catastrophic collapse, or something far more alien to our current models. The Big Pause is more than a thought experiment. It's a lens that forces us to see the universe as dynamic and fragile, its long-term behavior hinging on a delicate balance that we're only beginning to grasp. It's the still point in a turning cosmos, the deep breath before a future no one can fully predict. Think of the universe as the most intricate clock ever built, a cosmic timepiece without gears or springs, made instead of galaxies, dark matter, and the fabric of space-time itself. The ticking of this clock isn't marked by seconds or minutes, but by the steady pulse of expansion. Each tick is the increase in distance between far-off galaxies, a rhythm so constant and ancient that it has defined every moment since the Big Bang. Now imagine this. You're standing in a silent room with this great clock hanging before you, its pendulum swinging with absolute precision for 13.8 billion years. You've never known a moment when it wasn't moving. Then, in an instant, it stops. The pendulum freezes mid-swing, the ticking ceases, and the entire room is filled with an almost unbearable silence. In the real universe, this ticking is not just a metaphor. It's measurable in the way light stretches as it travels across space. Every beam of light from a distant galaxy is like a message carried across this ever-growing gulf. The farther it travels, the more it is redshifted, its wavelength stretched by the expansion of space itself. This is the heartbeat of the cosmos. And if expansion were to stop, that heartbeat would stop as well. The cosmic clock analogy works because expansion is tied to our concept of cosmic time. The ticks represent more than just motion. They represent the unfolding of the universe itself. When cosmologists speak about the age of the universe, they're really talking about how far this clock has been running since the Big Bang. A sudden halt in expansion is like freezing time in the largest possible sense. But here's the catch. In a stopped expansion universe, time would not literally stop for us locally. Our planet would keep spinning, days would pass, atoms would vibrate, and biological processes would continue. But cosmic time, the grand, large-scale measure of how space itself evolves, would suddenly take on a different meaning. Without expansion, that cosmic arrow would no longer point toward a more diffuse, colder, emptier future. The clock's hands might stop moving, but the gears inside, the smaller, local motions, would keep whirring. It's worth digging into why this would be so strange for physics. The expansion rate of the universe is encoded in a parameter called the Hubble constant, or, more accurately, the Hubble parameter, since it changes over time. Right now, it's about 73 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of separation between two galaxies, their recession speed increases by 73 kilometers per second. If expansion stopped, that number would drop to exactly zero. This is the equivalent of the second hand on our cosmic clock refusing to move. What would happen next? Without expansion, the entire framework of cosmology would need rewriting. The equations of general relativity that describe an expanding universe, the Friedmann equations, have terms for both expansion and contraction. If the expansion term dropped to zero, the balance between matter, radiation, dark matter, and dark energy would decide whether the clock starts ticking backward, a collapse, or remains perfectly still in an improbable cosmic stalemate. From our vantage point inside the universe, the effects would creep in slowly at first. Just as a stopped clock on the wall doesn't instantly throw your life into chaos, the end of expansion wouldn't be immediately obvious to casual observers on Earth. Astronomers looking at the most distant galaxies might notice that their redshift values stop increasing year after year. The faint stretching of ancient light from the cosmic microwave background would cease. Over centuries and millennia, our cosmic maps would stop evolving. The positions of the most remote galaxies would lock in place. There's also a philosophical layer to this clock analogy. Expansion gives us a sense of inevitability in cosmic history. It's why we can predict scenarios like heat death, Big Rip, or eternal acceleration. Without that motion, the future becomes much harder to read. A frozen pendulum doesn't tell you what's next. It only tells you that the mechanism that once governed everything has been interrupted. And that interruption would raise the most unsettling question of all: what stopped it? In the clockmaker's workshop, a stopped pendulum means someone touched it, or a gear broke, or the power source failed. In the universe's case, the only forces capable of halting expansion would be on the scale of cosmic law itself, a transformation in the nature of dark energy, a sudden reconfiguration of spacetime, or a shift in the underlying constants of physics. We would be forced to consider that the machinery of the universe is not eternal, but vulnerable to change. Now imagine you are a distant observer living in a galaxy far beyond the Milky Way, watching this same clock. From your perspective, too, the ticking has stopped. The universe is not expanding away from you any more than it's expanding away from us. And just like us, you would have to grapple with the implications. Is this a prelude to something? Is it a stable state? Or is the pendulum about to swing the other way? The cosmic clock analogy isn't just poetic. It's a warning about how deeply interconnected motion and time are in the universe. Halting expansion would be the most dramatic pause in history, a silence in the ticking that has guided the cosmos since its birth. And if that silence ever comes, it will mean the rules of the game have changed in ways we might not even be able to predict. To understand what keeps the universe expanding, and why stopping it would be so extraordinary, we need to dive into the mysterious engine behind it all: dark energy. Right now, the universe is in the midst of a battle between two colossal forces. On one side is gravity, the ancient architect of structure. Gravity gathers matter together, builds stars, sculpts galaxies, and tries endlessly to pull everything inward. On the other side is dark energy, an invisible, pervasive pressure that pushes everything apart, working against gravity on the largest possible scales. The truly strange thing? Dark energy isn't just holding gravity at bay. It's winning. Astronomers first realized this in the late 1990s while studying distant Type Ia supernovae, stellar explosions so bright and consistent in their luminosity that they can be used as standard candles to measure cosmic distances. The expectation was simple: if the universe had been expanding since the Big Bang, gravity should be slowing that expansion down. The farther away you looked, the slower galaxies should have been moving in the past. But when the measurements came in, they told a completely different story. The expansion wasn't slowing at all, it was speeding up. To explain this, scientists revived and repurposed an idea that even Albert Einstein had once played with: a cosmological constant. In Einstein's original use, it was a term in his equations to keep the universe static, before expansion was discovered. Today, the cosmological constant is interpreted as a form of energy inherent to space itself, what we call dark energy. If space has energy built into it, then as space expands, there's more space, and therefore more dark energy. The effect snowballs. The more the universe grows, the faster it grows still. One of the strangest properties of dark energy is that it appears to have negative pressure. In everyday terms, pressure tends to push things together, like air pressing against the inside of a balloon. But dark energy's negative pressure works in the opposite direction, accelerating the expansion of space itself. Imagine stretching a rubber band and discovering that instead of resisting you, it stretches faster the more you pull. That's what dark energy does to the universe. In the current cosmic budget, dark energy dominates. It makes up about 68% of the universe's total energy content. Dark matter, which still clumps under gravity and helps form galaxies, accounts for about 27%. Ordinary matter, the stuff that makes up stars, planets, people, and everything we've ever seen directly, is a mere 5%. This means the ultimate fate of the cosmos is, for now, being written almost entirely by this mysterious, invisible component. In the grand tug-of-war between expansion and contraction, gravity pulls harder where matter is dense, inside galaxies, inside clusters, but dark energy acts everywhere, even in the vast empty stretches between galaxy superclusters. And here's the key: on scales larger than those clusters, dark energy dominates completely, overpowering gravity's pull. Now, if we imagine the universe suddenly stopping its expansion, we're talking about breaking this dominance. For that to happen, either dark energy would have to vanish, weaken, or reverse into something that behaves more like attractive gravity, or something entirely new would have to appear to counteract it perfectly. In effect, you'd be rewriting the largest scale equation in existence. This is why the current expansion mechanism is so important to the thought experiment. The universe's accelerating growth isn't just a side effect of some old Big Bang momentum. It's being actively driven, right now, by whatever dark energy is. Stopping expansion would be like turning off the power source for an enormous, unseen engine that's been running for billions of years. And if you turned it off, you not only stop the motion, you'd remove the single greatest influence on the future shape of the cosmos. Dark energy is still a complete enigma. It could be a constant property of space, forever unchanging. It could be something that evolves with time, tied to fields and particles we haven't yet detected. It might even be a temporary phenomenon, destined to fade or transform into something else. But whatever it is the reason galaxies are fleeing from each other faster with every passing moment. Without it, the story of the universe's next billions of years would be completely different. And here's the paradox. We know dark energy exists only because of its effects on expansion, yet we have no direct evidence for what it actually is. If expansion were to stop, it wouldn't just be a change in cosmic behavior. It would be the loudest signal we've ever had that something fundamental about dark energy had changed or disappeared. It would be the ultimate clue to solving the mystery of what's been driving the universe all along. From the moment the universe was born, two great forces have been locked in a relentless contest. A cosmic tug-of-war that determines the fate of everything that exists. On one side you have gravity, the ancient, unyielding pull that binds planets to stars, stars to galaxies, and galaxies into vast clusters. On the other side is dark energy, an invisible force woven into the fabric of space itself, pushing outward and driving the expansion of the universe. This struggle has shaped every era of cosmic history, and it continues today, deciding whether the universe will expand forever, slow down, or, in the case we're imagining, stop entirely. In the earliest moments after the Big Bang, gravity held the advantage, but not in the way you might think. Just after inflation ended, that near-instantaneous ballooning of the universe in a fraction of a second, expansion was still happening at an incredible rate. Gravity acted like a cosmic brake, trying to slow it down. During those first hundreds of thousands of years, the universe was a dense soup of radiation, matter, and energy. Matter clumped together under gravity's influence, and over time, those clumps became the seeds of galaxies, stars, and planets. Back then, the density of matter was far greater than it is now. In cosmology, density is key to understanding the tug-of-war. The more matter there is in a given volume of space, the stronger gravity's pull becomes. In those dense early ages, gravity didn't have to fight nearly as much against dark energy because dark energy's influence was negligible in such small-scale, high-density conditions. But as the universe expanded, matter became more spread out, weakening gravity's grip on large scales. Dark energy, however, is different. If it's truly a property of space itself, its strength doesn't dilute as space grows. In fact, its effect becomes more pronounced as more space comes into existence. Imagine a rope-pulling contest in which one side gets weaker every minute while the other stays exactly the same. Eventually, the constant side will start winning. That's exactly what happened in our universe. For billions of years, gravity slowed expansion. Then, about 5 to 6 billion years ago, dark energy tipped the balance. Expansion, instead of continuing to decelerate, began to accelerate. This was the moment when the outward push overcame the inward pull for good, at least so far. On the largest scales, dark energy is now in control. The battle isn't uniform, though. On local scales, within galaxies and galaxy clusters, gravity is still the master. That's why galaxies don't get pulled apart by expansion. The Milky Way, for example, is held together by its own mass and the gravitational grip of dark matter, so it's not expanding internally. The same goes for the local group, the small cluster of galaxies to which we belong. But between these clusters, in the great cosmic voids spanning tens or hundreds of millions of light years, dark energy rules unchallenged. Space itself swells, carrying galaxies away from each other faster and faster. Now here's the intriguing part for our thought experiment. If the universe stopped expanding, it would mean this tug-of-war had somehow reached perfect balance. The push and pull would have to cancel each other exactly, an almost impossibly fine equilibrium. Or, alternatively, gravity would have found a way to overcome dark energy entirely, halting the expansion and perhaps setting the stage for contraction. Let's think about what that means in physical terms. In Einstein's general theory of relativity, the equations that describe the universe's expansion include contributions from both matter and radiation and dark energy. For expansion to stop, the sum of these contributions would have to equal zero. That balance isn't just unlikely, it's precarious. Any small fluctuation in density, or any change in the properties of dark energy, would break it. If gravity got slightly stronger, or dark energy slightly weaker, the universe would begin to collapse. If the opposite happened, expansion would resume. And there's a time element to all of this. The universe isn't static. Galaxies merge, stars explode, black holes grow, and matter shifts from one form to another. All of these processes subtly change the distribution of matter and energy, which in turn affects the balance. That's why cosmologists often say that a truly static large-scale universe is unstable. Without some deeper mechanism keeping it frozen, the cosmic tug-of-war almost always ends with one side gaining the upper hand. This struggle also determines what kind of universe we live in. Cosmologists classify possible universes based on their density and the strength of dark energy. A closed universe has enough matter for gravity to eventually win, causing a big crunch. An open universe has so little matter that expansion continues forever, possibly accelerating. A flat universe, the one we appear to live in, sits on the knife edge between these extremes, but dark energy's presence has tipped it toward endless acceleration. Stopping expansion would mean shifting this balance back to that knife edge or beyond, something current physics says is almost impossible without a fundamental change in the nature of reality. From a more visual perspective, you can imagine the universe's fate as a massive tug-of-war rope stretching between two teams. In the first few billion years after the Big Bang, gravity's side was winning. The rope was slowly inching toward them. Then, dark energy's team started pulling harder, not because they got stronger, but because gravity's team kept losing players as matter spread out. Now the rope is racing toward the dark energy side, faster and faster. For it to stop, someone would have to come in and grab the rope in the middle, holding it still against the pull of both sides, a feat that would require extraordinary intervention in the laws of the cosmos. In our current understanding, dark energy is constant. If it remains so, gravity will never regain the upper hand on large scales, and expansion will never stop. That's why this thought experiment is so radical. It assumes a fundamental shift in that constant, either it decays, transforms, or is cancelled out by an opposing effect. If such a shift occurred, the consequences would ripple through every level of cosmic structure. Galaxy clusters that are currently drifting apart would begin to feel each other's pull again. The boundaries of gravitational influence would expand, connecting regions of space that had been on the verge of slipping away forever. Over billions of years, the cosmic web, that vast network of filaments connecting galaxies, could begin to tighten, reshaping the large-scale architecture of the universe. And if gravity began to dominate, the tug-of-war wouldn't end in a stalemate. It would swing in the opposite direction. The universe could transition from expansion to contraction, setting the stage for a completely different endgame, a slow, inevitable collapse into the Big Crunch, where every galaxy, every star, every atom is drawn together into a final singularity. The cosmic tug-of-war isn't just a poetic metaphor, it's the fundamental mechanism deciding the ultimate destiny of everything. Right now, dark energy is pulling ahead, but in the scenario we're imagining, gravity somehow finds a way to dig in its heels, halt the retreat, and possibly begin the march back toward the center. When we talk about the expansion of the universe stopping, it's easy to imagine a sudden, dramatic freeze-frame moment. Galaxies hanging motionless in the void, stars suspended in place, like someone hit the cosmic pause button. But that's not what it would actually mean. The term, stopping, in this context refers to the large-scale expansion of space itself halting, not the complete cessation of motion within the universe. Galaxies wouldn't suddenly go dark and still, and stars wouldn't stop burning. The laws of motion would still apply, and local gravitational systems, like galaxies, solar systems, and planets, would continue to function as they do now. The difference lies in the cosmic scaffolding, the vast, ever-growing space between galaxies that is currently stretching faster and faster due to dark energy. Right now, the expansion means that distant galaxies are moving away from us at speeds proportional to their distance. The farther they are, the faster they recede. If that expansion stopped, the distances between galaxies on the largest scales would cease increasing. Instead of the cosmic fabric continuing to stretch, it would stabilize, locking in the arrangement of galaxies as they are at that moment in time. It would be like hitting the brakes on an accelerating car. The forward movement doesn't instantly reverse, but the acceleration is gone, and eventually, the speed evens out. In our universe, this would translate into a static large-scale structure, at least in terms of distance growth. Within galaxies, life would go on. Stars would continue orbiting their galactic centers, planets would keep circling stars, and black holes would still devour matter. The Milky Way and Andromeda, for example, are already gravitationally bound and on a collision course that has nothing to do with cosmic expansion. That fate would still be inevitable. On these smaller scales, gravity is already the dominant force, so halting expansion wouldn't change the basic choreography of these cosmic dances. However, on larger scales, the hundreds of millions or billions of light-years between galaxy clusters, things would shift dramatically. Right now, the expansion is strong enough that many galaxies are receding from each other so quickly that they will never interact. If expansion stopped, the boundaries of what could interact would be redrawn. Over incredibly long timescales, gravity could begin to reassert itself between some clusters that would otherwise have been forever separated. In theory, given enough time, we might see large-scale structures slowly start to pull together again, a process that's impossible under continued accelerated expansion. There's also a subtle but important consequence for the observable universe. As space expands, light from distant galaxies is stretched, pushing them into the redshifted darkness. Eventually, if expansion continues, many galaxies will slip beyond our cosmic horizon, disappearing from view forever. If expansion stopped, this slow disappearance would also cease. The galaxies we can see at that moment in time would remain visible for as long as their light continues to reach us. The night sky, on the grandest scale, would freeze in its content, though not in its dynamics. Stars would still form and die, supernovae would still flare, and cosmic structures would still evolve internally. This halting of expansion wouldn't erase the past. The cosmic microwave background, the fossil radiation from the Big Bang, would still be out there, whispering its 13.8 billion-year-old message. But its interpretation might change. Cosmologists build models of the universe's evolution based on the assumption of ongoing expansion. If it suddenly stopped, those models would have to be reworked. We would need to reconsider our understanding of dark energy. Perhaps it wasn't an eternal push after all, but a temporary phase. Such a shift in perspective could rewrite our cosmic history and predictions for the future. In a way, the stopping of expansion would mark a cosmic pivot point, a turning of the tide between two fundamental forces. For billions of years, the universe has been in an era dominated by expansion, where the large-scale motion of galaxies is driven not by gravity but by the stretching of space itself. Ending that would signal the dawn of a different age, one where gravity is no longer fighting a losing battle against the relentless growth of the cosmos. It would be the moment where the universe stops running away from itself. And yet, the immediate night sky would look almost exactly the same to us. That's the strange paradox. Such a profound shift in the universe's fate could happen without any visible drama from our vantage point. The sun would rise the next day. The moon would follow its cycle. Telescopes would still find distant galaxies right where they were yesterday. The big difference would be hidden in the math, in the measurements of redshift and distance that reveal the expansion rate. For the average observer, the stopping of the universe's expansion might be the quietest, most undetectable revolution in history. But for cosmologists, it would be the loudest possible alarm that our cosmic story has taken an entirely new turn. If the universe's expansion came to a halt, one of the first and most profound changes we'd notice, at least on a cosmological timescale, would be in the light we receive from distant galaxies. Today, as space stretches, the light waves traveling through it get stretched as well, increasing their wavelength and shifting them toward the red end of the spectrum. This is the cosmic redshift, and it's one of the fundamental observations that tell us the universe is expanding. But if expansion stopped, that gradual change in wavelength would freeze. Light from a given galaxy would no longer keep sliding toward the red. Instead, it would arrive at a fixed wavelength that corresponds to the exact state of the universe when the expansion stopped. This would be as if the great cosmic Doppler effect suddenly shut off, leaving the tone of the universe locked in place. The implications of this are deeper than they might seem. Redshift is not just a curiosity. It's the ruler and clock we use to measure the vast distances and histories of galaxies. Without it changing, astronomers would lose one of their most essential tools for tracking the dynamics of the cosmos. Every galaxy's light would essentially freeze in its current shifted state, and from that moment on, the redshift would no longer tell us how far away an object is moving from us. In fact, distances between galaxies would become static on the grand scale, which would force a fundamental rewrite of cosmology textbooks. The way we date events in the universe relies heavily on correlating redshift with time. Without a moving scale, it's like trying to tell time with a clock whose hands have stopped. There's another strange twist here. Even though the redshift stops changing, the light that has already been stretched will still arrive that way. For example, if a galaxy is currently 10 billion light-years away and its light has been stretched to a certain wavelength, that's how we'll keep seeing it from then on, no shorter, no longer. But no new stretching will occur. This means the look of the distant universe would become fixed in a peculiar way. Galaxies far away would appear as they did at the instant the expansion halted, frozen in both their light and their large-scale positions. They could still move under their own local gravitational influences, but the grand drifting apart that has shaped cosmic history for 13.8 billion years would vanish. In practical terms, astrophysicists would no longer observe the slow deepening of redshift that they've been recording for decades. Instruments like the James Webb Space Telescope or its successors wouldn't be able to track the tiny incremental changes in galaxy light that currently provide confirmation of cosmic expansion. The cessation would also remove the evidence stream that allows us to estimate things like the Hubble constant and dark energy's role. We'd still have all the data up to the stopping point, but beyond that, the universe's expansion history would become a fixed archive rather than a living process. Interestingly, the end of changing redshift could open the door to detecting other, subtler effects in light from deep space, signals that are normally drowned out by the dominant stretching of space. For example, minute gravitational influences from large-scale structures might become more apparent, because there'd be no background expansion constantly altering the wavelength. This could give us new insight into the web of cosmic filaments, dark matter distribution, and other phenomena that are hard to separate from the expansion signal today. However, it's important to understand that stopping expansion wouldn't immediately make the night sky look different to the naked eye. The changes in redshift happen so slowly that even over a human lifetime, they're virtually imperceptible without extremely precise measurements. What would change is the trend. Right now, every year, the universe's light shifts a little more red. In a stopped expansion scenario, that drift would be gone, replaced by a kind of eternal snapshot, in which the large-scale structure is frozen in its last expansion frame. This brings up a profound philosophical point. Redshift isn't just a number in an astronomer's notebook, it's part of the way we perceive cosmic time itself. Without it, our window into the ongoing evolution of the universe would be far more limited. It would feel, in a sense, as though the cosmos had stopped telling us a story it had been narrating for billions of years. We'd still see motion and change on smaller scales, stars forming, galaxies colliding, supernovae exploding, but the overarching drift of the great cosmic stage would be gone. The analogy might be like watching a movie where the background scene suddenly freezes while the characters in the foreground keep acting. It's still a story, but the sense of progression in the setting is gone. Without expansion, without evolving redshift, the big picture would no longer move forward. We would be in a kind of static universe when viewed on the largest scales, a place where the distances between galaxy clusters are fixed and the light they send us is forever stamped with the conditions of that final moment of growth. And perhaps most unsettling, if the redshift is no longer changing, then in some sense the arrow of time, at least as it applies to the universe's large-scale structure, has lost one of its most visible markers. Time itself would go on, of course, but the cosmic landscape would stop offering us clues about where we're headed. It would be as though we've stepped off the conveyor belt of expansion and now drift in a vast, still ocean, where all the ripples and waves are local, and the great tide that once carried everything apart has gone forever quiet. If the universe stopped expanding, one of the most subtle yet profound consequences would be in the way the night sky looks over immense stretches of time. Right now, we live in a cosmos that is not static. Galaxies are rushing away from one another, their positions shifting so slowly on human timescales that we never notice, but steadily enough that over millions or billions of years, the cosmic map changes. If expansion came to a halt, that grand dance would suddenly freeze at a large scale. The light from distant galaxies would still travel toward us, but their positions relative to each other in the vast cosmic web would no longer drift apart with each passing eon. Today, the expansion of space means galaxies are not just moving through space, but that the fabric of space itself is stretching, carrying them farther and farther away. This stretching subtly shifts their apparent positions in the sky, not like planets wandering across the constellations, but in an almost imperceptible way over unfathomable timescales. If that process ended, the current layout of the universe would lock into place. A galaxy 2 billion light-years away would remain exactly that distance away, forever, unless acted on by gravitational pulls from other structures. Future astronomers, peering through their telescopes, would find the same cosmic landmarks in exactly the same coordinates as their predecessors, a fixed atlas of the universe instead of a constantly evolving one. This would have an emotional and even philosophical weight. Humanity has always existed in a moving, shifting cosmos. Even if we couldn't see those changes directly with our eyes, we knew they were happening. Light stretched redder over time, galaxies slipped beyond our horizon of visibility. The very structure of the universe grew more diffuse with age. Without expansion, that sense of an unfolding cosmic story would vanish. Every patch of the deep sky would look identical generation after generation. While this might sound comforting, almost like the stability of a permanent cosmic ceiling, it would also rob us of one of the universe's most poetic features, its slow, inevitable transformation. The absence of expansion would also mean that galaxies currently on the brink of fading from view due to extreme redshift would stay visible forever, at least until their own light output dimmed naturally. In our expanding universe, each year pushes more galaxies beyond a point where their light can ever reach us again. It's as if the universe keeps turning out the lights in the far corners of the cosmic theater. But if the expansion stopped, the lights would stay on. That final frame of the cosmic movie would remain illuminated indefinitely, preserving a far richer view of the universe for future civilizations than what would otherwise survive. Over extremely long timescales, however, the fixed sky would not be completely static. On smaller scales, local motions would still happen. The Andromeda Galaxy would still collide with the Milky Way in a few billion years, reshaping the night sky dramatically for anyone around to see. Galaxy clusters would still churn internally, with members moving around their shared gravitational center. But on the vast, intercluster scale, the arena where expansion truly dominates, the big picture would remain unchanged. The cosmic background would essentially be a photograph pinned to the wall of time. This unchanging sky could alter the way civilizations think about the universe. Today's astronomy is driven by the idea that the cosmos has a history we can reconstruct, a past of smaller, closer galaxies and a future where the majority will disappear beyond a cosmic event horizon. If expansion froze, so would that evolutionary narrative. Instead of being historians of an ever-receding universe, astronomers would become cartographers of a fixed celestial map. Cosmic archaeology, studying the distant past through light that has traveled for billions of years, would still be possible, but the sense of urgency to catch disappearing galaxies before they vanish would be gone. The view would be permanent, timeless, and oddly serene. The implications reach further than just stargazing. A halted expansion could signal a deeper change in the underlying physics of the universe, perhaps a shift in dark energy, or a cosmic balance where matter's gravity exactly cancels out the outward push of expansion. If that balance held forever, the universe's visual face would remain steady indefinitely. But if it were just a pause before contraction began, then that fixed sky would be the calm before an even more dramatic transformation, a tightening of the cosmic web, the drawing together of galaxies, and eventually the slow disappearance of that fixed map into a brighter, hotter, and more crowded sky. In that moment, future beings would stand beneath a cosmic ceiling that is no longer a fleeting frame of an endless story, but the final act held in suspension. The idea that you could look up at the stars and know that someone a million years from now would see exactly the same picture is both comforting and unsettling. It would mean the universe had entered a state unlike anything in its previous 13.8 billion years, a universe that no longer drifts apart, but simply exists, unmoving on the largest of scales, as though time itself has let go of its grip on space. If the universe were to stop expanding, one of the most profound changes would be in the fate of the cosmic microwave background, the faint afterglow of the Big Bang that currently bathes the entire cosmos. Today, this radiation is incredibly cold, only about 2.725 Kelvin above absolute zero, and it continues to cool ever so slightly as the universe expands, its wavelengths stretching further into the microwave range and beyond. This gradual cooling is not something we can see happen in real time, but over billions of years, it transforms the CMB into an ever fainter whisper of the universe's fiery birth. However, if expansion stopped, that cooling process would come to a complete halt. The wavelengths of the photons making up the CMB would stop stretching, freezing them in their current state. The temperature of the CMB would stabilize, forever locked at whatever it happened to be at the moment expansion ceased. It would no longer slide toward longer, colder wavelengths. Instead, the background radiation would become a permanent fixture of the cosmic environment, like a faint, eternal glow from an ancient fire that can never fade further. In the expanding universe we live in now, the CMB acts as a cosmic clock, telling us how long it has been since the Big Bang and showing us how the universe has evolved. As its temperature drops, we can predict and measure the passage of cosmic time. But if that cooling froze in place, it would be as if someone pressed pause on that clock. For scientists far in the future, there would be no gradual shift to measure, no way to tell whether a million years or a billion years had passed since the halt occurred, at least not by looking at the CMB's temperature alone. The very tool we use to map cosmic history would lose one of its most important functions. This frozen CMB would also subtly change the conditions for everything else in the universe. Right now, the cosmic microwave background is so faint that it has almost no effect on the behavior of matter, stars, or galaxies. But it is still there, adding just a tiny bit of heat to the vast cold of intergalactic space. In a static universe, this background would remain an eternal thermal bath, a constant, faint blanket of energy. Over unimaginable timescales, that tiny but permanent warmth could influence the way extremely cold objects, like rogue planets or dust clouds drifting in the darkness, radiate and exchange energy with their surroundings. There's also a psychological and philosophical twist. For the entire history of the universe, the CMB has been fading, a symbol of the cosmos's slow march toward heat death. It tells us that everything is cooling, slowing, and moving toward stillness. If that cooling stopped, it would mark a strange turning point, a universe where the ancient afterglow never fades further, where the echo of the Big Bang is preserved at the same brightness for eternity. It would be a constant reminder of the moment expansion ceased, as if the cosmos itself had frozen in mid-breath. For astronomers in such a universe, the CMB would no longer be a changing backdrop but a permanent ceiling to their measurements. The data from it would always be the same, decade after decade, millennium after millennium. Our current cosmology is built on change, galaxies drifting apart, the CMB cooling, structures evolving. Without expansion, that dynamic view would vanish, replaced by an eerily static universe where the past still glows but never changes. And in a way, that might make the universe feel smaller. Right now, looking at the CMB is like peering through time, back to the earliest moments of creation. Its shifting spectrum tells us that the story is still unfolding. But if that spectrum stopped evolving, it would be like a photograph hanging in a museum, still breathtaking, still full of meaning, but frozen forever, no longer part of a living story. It would mean the cosmos, in some sense, had stopped telling time. If the expansion of the universe were to suddenly stop, one of the most profound changes would not simply be in the structure or movement of galaxies, but in our very perception of time itself. Right now, our concept of cosmic time is deeply tied to the universe's expansion. In cosmology, time isn't just the ticking of a clock, it's the parameter that describes how the universe evolves. The very idea of the age of the universe comes from measuring how long it has been expanding since the Big Bang. If expansion halted, this forward motion in the cosmic timeline would shift from a dynamic unfolding to something eerily static. At present, the passage of cosmic time is tied to measurable changes in the universe. Galaxies drift further apart, the cosmic microwave background cools, and large-scale structures evolve. Without expansion, these benchmarks for the flow of time would vanish. The universe would stop stretching, so cosmological redshift, the gradual stretching of light from distant galaxies, would cease. Our primary indicator of deep time progression in astronomy would be gone. We could still measure local processes, like the burning of stars or the decay of unstable isotopes, but the universal clock, that has been ticking for 13.8 billion years, would no longer feel like it's ticking at all. On a more theoretical level, expansion is deeply tied to the thermodynamic arrow of time, the reason we perceive time as flowing in one direction. The arrow of time is largely defined by the increase of entropy, the measure of disorder in a system. In an expanding universe, entropy has more room to grow because new space is constantly being created. This allows for more ways that matter and energy can arrange themselves, which keeps the arrow of time moving forward. If the expansion stops, the growth of entropy could slow dramatically. That doesn't mean time would stop in the literal sense, but it would feel less dynamic on a cosmic scale, as the universe's capacity for new arrangements would be capped. Some physicists speculate that without expansion, the arrow of time might even become harder to define, especially if large-scale cosmic processes settle into long-lived equilibrium states. There's also the question of how halting expansion would affect the fundamental link between time and energy. In quantum mechanics, time and energy are conjugate variables, connected by the uncertainty principle. Over cosmic distances, expansion changes the energy of photons, stretching them, reducing their frequency, and thus lowering their energy over time. This is a direct manifestation of how time and energy interplay in a dynamic universe. If expansion froze, photons would stop losing energy to redshift. The total distribution of energy in the universe would become fixed in a way that hasn't happened since moments after the Big Bang. Cosmic time, as measured through changes in the energy of radiation, would essentially plateau. From a relativistic standpoint, the very geometry of space-time would shift. Expansion changes the way space-time curves on large scales, and this curvature affects how time passes in different regions of the universe. A universe that isn't expanding would have a static large-scale geometry, potentially causing cosmic time to behave more like Newtonian absolute time, uniform everywhere, without the same evolving distortions we see in a dynamic space-time. This would strip away some of the relativity we currently expect in cosmic measurements, leading to a universe where the background, fabric, is no longer actively changing. For observers like us, who experience time through motion, change, and causality, this could be psychologically and scientifically disorienting. We might find that the concept of a cosmic future loses meaning. Without expansion, there would be no new horizons forming, no galaxies disappearing beyond the reach of light, no changing backdrop against which we measure our place in the cosmos. Everything visible today would remain visible indefinitely, until local astrophysical processes altered it, locking the universe into a strange kind of temporal stasis. It's not that stars wouldn't age or die. Those processes are driven by local physics, not cosmic expansion, but the large-scale, universe-wide evolution would freeze. It would be like pausing the film reel of the cosmos while some small objects inside the frame kept moving. On human timescales, such a change might feel subtle at first. We would still see stars being born, exploding, and fading. Galaxies would still collide under gravity. But the deeper sense of being in an evolving universe, one whose scale itself is a function of time, would be gone. Over billions of years, this static cosmic scale would likely reshape how any surviving civilizations understood history. Without expansion as a clock, they might anchor time measurement solely to cycles of local stars or planetary orbits, losing the broader sense of a universe-wide unfolding story. Philosophically, halting expansion raises unsettling questions about whether time is an intrinsic feature of reality, or simply a measure of change. In a non-expanding universe, if all large-scale change halted, would time still flow in the same way? Could the universe exist in a kind of timeless state, where the concept of past, present, and future only applies to small, localized processes rather than the cosmos as a whole? Some theories in physics even suggest that time might be emergent, that is, not a fundamental property of reality but something that arises from change. If that's true, stopping expansion could strip away a huge part of what gives rise to time as we perceive it. The implications reach into the realm of energy conservation as well. In an expanding universe, energy conservation doesn't work the same way it does in a static one. For example, photons lose energy due to redshift, and that lost energy isn't transferred anywhere, it simply ceases to exist in the same form. In a static universe, energy conservation would behave more traditionally, with no large-scale mechanism draining photon energy. This would change not only the fate of light but also how the laws of physics are expressed on cosmic scales. Over long time scales, the difference would be monumental. Radiation would retain its energy indefinitely, and the background glow of the cosmos would not fade into near absolute darkness as it would in an ever-expanding scenario. In essence, stopping expansion would be like flipping a switch on the universe's grand clockwork. The ticking wouldn't cease entirely. Local processes would still unfold, but the deep, slow rhythm of the cosmos itself would go silent. Without that rhythm, time would become a far more local, subjective experience, and the connection between time and the evolving energy of the universe would be severed. For a civilization that has learned to measure billions of years and watch the universe itself grow, this would be like waking up one morning to find that the seasons, the tides, and the movement of the stars had all stopped, not because the world ended, but because the largest scale motions had simply decided to rest forever. If the expansion of the universe were to stop, the balance of cosmic motion would change dramatically, and that shift would have a profound influence on how stars are born. Right now, the expansion of space plays a subtle but crucial role in moderating the frequency of galaxy collisions. Galaxies are constantly moving under the influence of their mutual gravitational pulls, but because the universe is expanding, there's an additional factor stretching them apart over vast distances. This cosmic stretching means that while galaxy mergers do happen, they occur less often than they would in a universe without expansion. If the expansion stopped entirely, galaxies would no longer be carried away from one another by the metric growth of space. Gravity, being relentless and long-ranged, would dominate over larger scales, pulling massive structures toward one another far more effectively. The result would be a universe that is far more dynamic and violent on galactic scales. Without the safety cushion of expansion, clusters of galaxies could collapse inward more quickly, leading to a dramatic rise in galaxy collisions. Every time two galaxies pass close enough, their mutual gravity distorts them, dragging out immense tidal tails of stars and gas. If the interaction is strong enough, the galaxies can merge entirely, combining their masses and forming a single, often much larger, galaxy. These mergers can be spectacular triggers for star formation. When galaxies collide, clouds of interstellar gas within them get compressed, causing vast regions of molecular hydrogen to collapse into new stars. This process is sometimes called a starburst, because the rate of star formation skyrockets to many times its usual pace. In our currently expanding universe, starburst galaxies are relatively rare and often short-lived phases in a galaxy's life. But in a universe with no expansion, starbursts could become the norm rather than the exception. Imagine looking into the night sky and seeing not the serene spirals and ellipticals we know today, but a chaotic tapestry of distorted, merging galaxies lit up with the blue-white light of countless newborn stars. These young stars would be hot and bright, but they would also burn through their fuel quickly, living only a few million years before ending their lives in supernova explosions. As a result, the universe would be punctuated by frequent, dazzling bursts of light as massive stars died violently, enriching the surrounding space with heavier elements. Over cosmic timescales, this accelerated star formation would have consequences for the composition and evolution of galaxies. In our current reality, galaxies form stars at a measured pace, gradually depleting their gas over billions of years. But in a non-expanding universe, they might burn through their reserves much more quickly. A galaxy could exhaust its cold gas supply in a fraction of the time, leading to an earlier transition from a vibrant, star-forming system into a red and dead, elliptical galaxy dominated by old stars. This would fundamentally change the timeline of cosmic evolution. Instead of having galaxies actively forming stars for many billions of years into the future, much of the stellar birth could happen in a relatively compressed era following the halt of expansion. Another subtle shift would occur in the types of stars being formed. In violent starburst environments, the conditions often favor the creation of more massive stars than in calmer, quiescent galaxies. Massive stars influence their surroundings in powerful ways. They emit intense ultraviolet radiation, produce fierce stellar winds, and explode as supernovae, all of which can disrupt nearby gas clouds and trigger further waves of star formation. This feedback loop could create an even more turbulent and unstable cosmic environment. At the same time, the heavy elements forged in these massive stars would rapidly enrich the interstellar medium, making future generations of stars more metal-rich. This enrichment process, which in our universe has taken billions of years, could be greatly accelerated. The clustering of galaxies would also evolve differently in a universe without expansion. Right now, cosmic structures like the cosmic web of filaments and voids are slowly growing as gravity draws matter together, but this growth is counteracted by the accelerating expansion caused by dark energy. Without expansion, the balance tips entirely toward collapse. The great filaments of galaxies could contract, feeding material into massive nodes where colossal mergers occur. In these dense regions, starburst activity could become so extreme that entire galactic clusters blaze with the light of countless new stars, outshining everything else in the universe. The increased density of galaxies in these regions would make gravitational interactions and mergers even more frequent, reinforcing the cycle. However, there's a long-term catch to this burst of cosmic creativity. The universe's total supply of cold gas suitable for star formation is finite. In our current expanding universe, the slow pace of star formation means this gas will last for many billions of years before it's mostly locked up in stars and stellar remnants. But in the collision-heavy environment of a static universe, gas would be converted into stars far more quickly, leading to an earlier onset of the so-called degenerate era of the cosmos, a time when no new stars are forming, and the universe is lit only by the aging glow of long-lived red dwarfs. In this sense, stopping expansion could create a short-lived era of brilliance followed by a much darker and quieter future. Even the shape and size of galaxies could be different. Mergers tend to transform spiral galaxies into massive ellipticals, so over time the familiar spiral arms we see in the Milky Way and other galaxies might become a rarity. Instead, most galaxies would be giant, featureless ellipsoids filled with older stars and little fresh gas. The diversity of galaxy shapes might diminish, replaced by a universe dominated by huge, ancient, and inactive galactic structures. This would change the overall aesthetic of the cosmos on a grand scale. The interplay between increased collisions and accelerated star formation would also have ripple effects on black hole growth. When galaxies merge, their central supermassive black holes often merge as well, creating even larger ones. The gas driven toward these black holes during mergers can feed them at incredible rates, making them flare up as quasars, brilliant beacons visible across cosmic distances. With more frequent mergers, the quasar population could spike dramatically, filling the universe with intense radiation that might even influence the formation of smaller galaxies nearby by stripping away their gas. In essence, halting the expansion of the universe would turn the cosmic dial toward a far more active and chaotic state in the short to medium term, but at the cost of burning through the universe's star-making fuel much more quickly. It would be a cosmos of spectacular violence and beauty, where the night sky is filled with the light of countless newborn stars and the afterglow of their explosive deaths, but it would also be a universe that ages faster, racing toward a quieter and emptier destiny. If the universe's expansion were to come to a complete stop, the large-scale ballet of galaxies across the cosmos would undergo a profound change. In our current era, the accelerating expansion caused by dark energy is slowly pulling galaxies apart, stretching the vast distances between them and making interactions less likely over immense timescales. But in a static or even contracting cosmos, this outward push would vanish, and the only dominant large-scale force left would be gravity. Galaxies that were once on diverging paths would instead find themselves subtly but inevitably drawn toward one another. Over millions and billions of years, this shift in cosmic dynamics would radically alter the architecture of the universe. In the absence of expansion, the gravitational attraction between galaxy clusters would become more pronounced. Right now, expansion acts like a vast cosmic tide, opposing the pull of gravity over the largest scales. Remove that tide, and the small gravitational tugs between galaxies begin to matter much more. These pulls, though weak at great distances, are persistent, and in a universe with infinite patience, they would ultimately bring more and more galaxies together. The cosmic web's filaments would tighten, the great voids might start to shrink, and the large-scale distribution of matter would slowly clump into fewer, denser regions. For nearby galaxies, the effect would be even more dramatic. Imagine the local group, our neighborhood containing the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of dwarf galaxies. Currently, Andromeda is already on a collision course with the Milky Way, set to merge in roughly 4 billion years. With expansion halted, such mergers wouldn't just be occasional cosmic events. They would become the natural destiny for almost every galaxy pair close enough for gravity to have a foothold. The pace of this galactic migration would accelerate on geological and astronomical timescales, leading to a universe where isolated galaxies become a rarity. Clusters of galaxies would grow larger and denser as formerly distant members drift inward. In the current expanding universe, clusters are bound systems, but their outskirts are influenced by the Hubble flow, slowly stretching them apart. Without expansion, those outskirts would collapse inward, drawing in more galaxies from the surrounding cosmic web. Over time, small groups would fall into larger clusters, and clusters would merge into enormous superclusters. The eventual outcome could be a universe dominated by a relatively small number of ultra-massive galactic conglomerates, each a sprawling city of stars and dark matter, holding trillions of suns. These mergers wouldn't be peaceful affairs. As galaxies approach, tidal forces would distort their shapes, pulling out vast streams of stars, gas, and dust into long, sweeping tails. Collisions would compress interstellar gas clouds, triggering bursts of star formation. Massive new stars would flare to life in bright blue clusters, briefly outshining entire galaxies before dying as supernovae and enriching the surrounding space with heavy elements. Black holes at the centers of merging galaxies would also spiral toward one another, eventually coalescing in some of the most energetic events the universe can produce, sending gravitational waves rippling through space-time. The skies of planets orbiting stars in these future galactic cities would be breathtaking, dense with stars, nebulae, and glowing tidal streams stretching across the heavens. Yet this beauty would come at the cost of cosmic diversity. Over immense spans of time, as galaxies continue to merge, many of the smaller, unique galactic forms we see today, grand design spirals, irregular dwarfs, and delicate lenticulars, would vanish into the homogeneity of massive elliptical galaxies. These giant ellipticals would dominate the landscape, each containing the history of countless smaller galaxies blended together into one. Dark matter, too, would play a central role in this transformation. Invisible yet dominant in mass, it would act as the framework upon which these mergers unfold, guiding galaxies along gravitational filaments into deeper wells of potential. Over time, the dark matter halos of colliding galaxies would merge, deepening the gravitational potential wells and making it even harder for stars, gas, or any material to escape. The result would be increasingly compact, tightly bound galactic superstructures. On a long enough timeline, these growing galaxy conglomerates might even begin to merge with one another, further reducing the number of distinct structures in the universe. If no other major cosmological shifts occurred, no resurgence of expansion, no catastrophic collapse, the ultimate fate could be a cosmos where only a handful of hypermassive structures drift through the dark, each the product of countless mergers over eons. Such a universe would be a stark contrast to the one we see today, with its billions of galaxies scattered across space like cosmic islands. Instead, it would be more like a sparse archipelago of a few titanic continents, separated by vast gulfs of darkness. This gravitational clustering could also have consequences for the cosmic background radiation. As more galaxies merge and clump together, large-scale gravitational fields could slightly distort and shift the energy of background photons, producing subtle but detectable imprints. These changes might serve as a historical record for any future astronomers, if intelligent life still exists, allowing them to piece together how their cosmos evolved from a once-expanding universe into one where gravity reigns supreme. The shift toward increased galaxy mergers would also accelerate the pace of cosmic aging. With so many collisions and starbursts triggered in quick succession, available gas reserves for star formation would be consumed more rapidly. In our universe today, star formation is already slowing as galaxies run out of cold gas. In a merger-dominated cosmos, this process would speed up, meaning the bright, active era of the universe might end sooner. Over time, without fresh gas to form new stars, these massive galaxies would fade into collections of long-lived, dim red dwarfs and ancient stellar remnants, white dwarfs, neutron stars, and black holes, glimmering faintly in the dark. Yet even in such a fate, there would be moments of drama. Binary star systems disrupted by the chaotic gravitational environments of dense galactic cores could be flung into intergalactic space, becoming rogue stars drifting in the dark. Supermassive black holes and merging galaxies could sling entire star clusters outward at thousands of kilometers per second. And the occasional collision of compact objects, like neutron stars or black holes, would still produce bursts of energy visible across the cosmos. These would be rare compared to the early fireworks of galactic merging, but in a dark, quiet universe, they would stand out as some of the last great cosmic events. If the universe stopped expanding, this gradual gravitation-driven transformation would be unstoppable. What began as a subtle shift in the balance between expansion and gravity would, over billions and trillions of years, completely reshape the cosmos. The universe would grow smaller in terms of the number of independent galactic structures, but denser and more intricate in its local architecture. The sky would fill with closer, brighter neighbors, until eventually, only a handful of colossal galactic metropolises remained, shining faintly in the ever-encroaching dark. If the universe stopped expanding, the night sky would slowly become a living record of this new cosmic intimacy. At first, things would appear mostly unchanged. Our familiar constellations would still decorate the heavens, planets would still make their slow dances across the zodiac, and the Milky Way would still spill its shimmering arc overhead. But given enough millions, then billions, of years, subtle changes would creep in, changes so gradual that no single generation would witness the full transformation, yet so monumental that future civilizations might be astonished at historical images of a sparser sky. With cosmic expansion halted, galaxies that were once receding from us would now be held in place, no longer carried away by the stretching of space. Gravity would have a chance to assert itself on scales it never could before, pulling distant island universes toward one another. Over vast stretches of time, more and more galaxies would drift closer to the local group, and the sky would grow richer with points of light, each not a star, but billions of stars bound together in galactic form. Imagine looking up and seeing not just a faint smudge of Andromeda, but multiple bright swirls of spiral arms across the horizon, glowing with the combined light of countless suns. The sky would become busier, almost crowded, like a city skyline where the buildings are galaxies. As these galaxies approached, some would be bright enough to be seen even in broad daylight, glowing faintly against the blue sky like the moon does now, though smaller. At night, they would dominate, giant glowing disks with fine details visible to the naked eye, like the delicate spiral of M51 or the bar of NGC 1300. For early astronomers of that future, telescopes might become less about finding faint fuzzies in the dark and more about studying the intricate structures of galaxies so close you could almost imagine flying to them. But this era of abundance would not last forever. As galaxies merged and star formation peaked in great bursts of activity, the cosmos would briefly become more brilliant than ever before. In every direction, regions of intense stellar nurseries would blaze in infrared and ultraviolet light. New stars, massive, hot, and short-lived, would be born in staggering numbers, their lights spilling across space. The night sky would be alive with newborn suns and exploding supernovae, making it perhaps the brightest, most vibrant age the universe had ever known since its youth. Yet, the very process that would make the sky so alive would also set the timer for its slow death. Massive stars burn fast and die young, and in these crowded, merged galaxies, they would go supernova by the millions, leaving behind neutron stars and black holes. Star formation, fueled by vast clouds of gas, would consume that fuel quickly. After the fireworks of cosmic mergers, the supply of cold hydrogen would dwindle. Without new fuel, the great galactic cities would go dark, no new stars to replace the old. Over billions of years, the night sky would shift from an overcrowded tapestry of bright spirals and blazing star clusters to a quiet, dim expanse populated mainly by long-lived, faint red dwarfs. The dazzling spirals would fade into amorphous blobs as star formation ceased and only ancient stars remained. The sky would still be filled with galaxies, perhaps more than ever before, but they would no longer shine with youthful vigor. Instead, they would resemble cosmic graveyards, vast collections of stellar remnants, glowing faintly like dying embers. Eventually, even these would fade. The last red dwarfs would burn slowly for trillions of years, but in time, they too would exhaust their fuel. By then, the bright age of the cosmos would be a distant memory, recorded in whatever civilizations managed to endure the changing tides of the universe. Future astronomers might study ancient archives and marvel that there was once an age when the night sky was so full of light that darkness was rare. In this way, a universe without expansion would give us both extremes. First, an era of brilliant, crowded skies filled with galactic fireworks. Then, a long twilight, where the abundance of galaxies in the sky would be a silent reminder of the light that once was. It would be a cosmic rise and fall played out on the grandest stage imaginable. An endless night that began brighter than ever, only to end in shadows. If the universe were to stop expanding, one of the most intriguing implications would be its potential effect on the long-term thermodynamic fate known as heat death. Heat death describes a state in which the universe has reached maximum entropy, a condition where all energy is evenly distributed, and no work can be done because there are no longer differences in temperature, pressure, or density to drive processes. In our current understanding, under continuous expansion, galaxies move apart at accelerating speeds, energy becomes more diluted, and eventually even the most energetic particles spread so far from each other that interactions become exceedingly rare. This leads to an extremely cold, dark, and static universe where nothing changes. However, if expansion were to stop completely, the mechanisms driving us toward heat death would be altered dramatically. With expansion halted, the distances between galaxies would no longer increase. This means the energy density of the universe would not continue to drop at the same relentless pace. Matter and radiation would remain at closer distances, and cosmic structures would interact more frequently than they would in an endlessly expanding scenario. As a result, the process of reaching maximum entropy could be slowed, potentially by vast orders of magnitude. In our accelerating universe, dark energy plays the role of pushing galaxies apart faster over time. The faster expansion proceeds, the less chance there is for large-scale structures to interact. But in a non-expanding universe, dark energy's influence would be effectively neutralized, or, in some hypothetical models, completely gone. Gravity would then dominate over large distances, allowing interactions that would otherwise never happen in an accelerating cosmos. Galaxy collisions, black hole mergers, and star-forming events would continue far longer than currently projected, injecting fresh order, in the form of new structures, into the universe and resetting, in small ways, the march toward equilibrium. Another significant factor is temperature. In a constantly expanding universe, the cosmic microwave background (CMB), the faint afterglow of the Big Bang, continues to cool as space stretches. It started at thousands of degrees Kelvin in the early universe, but has now cooled to just 2.725 K. In an expanding future, this cooling continues indefinitely. But if expansion halts, the CMB would still cool somewhat due to ongoing processes, but the rate of cooling would slow dramatically. The background temperature would level off over extremely long periods, preventing the universe from plunging as rapidly toward absolute zero. That residual warmth might seem insignificant compared to the scorching past of the cosmos, but in thermodynamic terms, even a slight difference in average temperature across the cosmos can delay the point of complete equilibrium. This change in trajectory would also affect the life cycles of stars. In the current model, as expansion progresses and galaxies drift apart, new star formation slows because the raw material, dense clouds of gas and dust, becomes harder to compress into new stars. Without expansion, gravitational forces could keep recycling material within galaxies and between merging galaxies for far longer. Massive galaxy mergers would replenish star-forming material, causing bursts of new stellar generations. These stars would inject light, heat, and structure back into the universe, keeping entropy slightly lower than it would be otherwise. While the second law of thermodynamics would still guarantee an eventual march toward disorder, these bursts could extend the process by trillions, or even quadrillions, of years compared to our current projections. Black holes would also have a different fate in such a scenario. Under expansion, most black holes become isolated over unimaginable distances, eventually evaporating through Hawking radiation over vast timescales. But in a static universe, they would be far more likely to interact with surrounding matter, consuming stars, gas clouds, and even other black holes at higher rates. Each merger would release immense amounts of gravitational wave energy, locally reducing entropy temporarily by creating new high-energy systems. Furthermore, the infall of matter into black holes converts mass into radiation, reintroducing usable energy into the surrounding space, something that in an expanding universe becomes increasingly rare. This energy could keep small-scale processes running far longer. One might imagine that such a delay in heat death would give the cosmos a second wind, a prolonged middle age where galaxies remain vibrant, stars are plentiful, and energetic processes continue to shape the universe. Over these extended eons, civilizations, if any exist, might find themselves in a universe that is far more hospitable for much longer than in our current predictions. A slower drift toward entropy could give life, technology, and culture more time to evolve, adapt, and perhaps even find ways to manipulate cosmic conditions. But it is important to understand that delayed does not mean avoided. Even without expansion, the supply of usable energy is finite. Stars still consume their fuel, even if the fuel supply is replenished periodically by mergers. Black holes still radiate away their mass, even if at a glacial pace. Over truly vast timescales, numbers with dozens of zeros beyond human comprehension, the universe would still reach a state of maximum entropy. The difference would be that the journey to that state would be far richer in events, more interactive, and far less lonely than the cold, isolated future we envision in an accelerating universe. Interestingly, some cosmological models suggest that if expansion stopped not just temporarily but reversed, leading to a slow contraction, heat death, as we know it, might never occur at all. Instead, matter and energy could be reconcentrated over time, possibly leading to new phases of cosmic evolution, or even a new Big Bang. In such cyclic models, entropy is not simply an ever-increasing monotonic quantity. Instead, it is reset or restructured periodically. In that case, halting expansion could be the first step toward a universe that perpetually regenerates itself. Ultimately, the end of cosmic expansion would not be a simple switch that freezes the universe in its current state. It would profoundly change the balance between order and disorder, between activity and stillness. The vast, dark, lonely heat death predicted under infinite expansion might give way to a slower, more interactive decline, where gravitational encounters, star formation, and high-energy events continue for far longer than anyone in our accelerating cosmos could expect. It would be as if the universe, instead of quickly dimming into silence, lingered at twilight, letting the lights burn for ages before the final darkness fell. If gravity were to gain the upper hand once cosmic expansion stopped, the balance of the universe could shift in a dramatic and potentially catastrophic way. At present, the expansion of the universe, driven by dark energy, is steadily increasing the distance between galaxies, countering the inward pull of gravity. But if that expansion halted, gravity would no longer be opposed on the largest scales. Given enough time, this imbalance could mean that galaxies, galaxy clusters, and even the largest cosmic structures would start to draw together instead of drift apart. This slow process might take billions or even trillions of years, but the cumulative effect could eventually lead to a full-scale reversal of the expansion. As gravity began to dominate, the universe's structure would change on unimaginable timescales. The largest voids would start to shrink as matter migrated toward denser regions. Galaxy superclusters would condense further, their contents spiraling toward common centers of mass. As distances between galaxies decreased, collisions would become far more frequent. The immense gravitational forces during these mergers would ignite bursts of star formation in some cases, while in others, black holes would feast on the infalling matter, growing to colossal sizes. Over time, the cosmic web, the delicate network of filaments and voids that defines the universe today, would begin to tighten and fold inward. Eventually, this tightening would extend beyond clusters and filaments to the universe as a whole. On the largest scale, every piece of matter would start to move toward every other piece. If this inward movement continued unchecked, the universe could enter a runaway collapse phase. Galaxies that were once millions of light-years apart would close the gap over vast timescales, and as they merged, the overall density of the universe would rise. The increased density would also mean a rise in temperature, as gravitational potential energy was converted into heat. In the distant future of such a collapse, radiation would grow more intense, and the night sky could shift from dark and tranquil to an increasingly bright and energetic place, until things took an even more extreme turn. As collapse progressed, the distances between everything, stars, planets, black holes, would shrink, and the energy in the universe would become more concentrated. Physics predicts that if this process continued without interruption, it could culminate in what's called a big crunch, a moment when all matter, radiation, space, and even time itself would compress into an incredibly hot, dense state. This would essentially be the reverse of the Big Bang. The very fabric of space-time would curve inward, converging toward a singularity-like state where current physical laws break down. In this final stage, the temperatures and densities could rise to levels far beyond anything experienced since the first moments after the Big Bang, potentially reigniting conditions similar to the birth of the universe. Whether a big crunch would truly occur depends heavily on the amount and distribution of matter, the strength of gravity compared to other cosmic forces, and the behavior of dark energy. If dark energy were to completely vanish or change its nature into something that worked with gravity instead of against it, collapse might be inevitable. Alternatively, if dark energy weakened only slightly, the collapse could still happen, but over such prolonged timescales that it would be nearly impossible for any civilization, even one with billions of years to prepare, to survive long enough to witness the final stages. This possible end scenario is deeply intertwined with other cosmic fates. For instance, if collapse occurred quickly, it might preempt the slow fade toward heat death by recycling all matter and energy into a new singular state. Some speculative theories even suggest that such a collapse could trigger another Big Bang, starting a new universe with its own laws of physics, a cosmic cycle of birth, death, and rebirth. In that case, the universe stopping its expansion wouldn't just mark the end of cosmic growth, but the first step toward a new beginning. However, whether such a rebirth is possible or whether collapse would truly lead to an ultimate end remains one of the great unanswered questions in cosmology. If the universe were to halt its expansion and begin contracting, the shift wouldn't be instant. It would unfold over billions of years, almost imperceptible at first. Galaxies that once seemed fixed in their recession would start slowing, then reversing course. From any given point in the cosmos, the vast tapestry of space would appear to pull inward, as if the universe itself were breathing in after an eternity of exhalation. The large-scale structure, the cosmic web of filaments and voids, would tighten. Clusters of galaxies, once separated by incomprehensible gulfs, would start to converge, pulled together by the relentless force of gravity. Initially, this might even be beautiful in a haunting way. The night sky would grow richer as galaxies moved closer, their light more concentrated and brilliant. But this beauty would mask a darker truth. Each approach would bring with it the seeds of destruction. Collisions between galaxies would become more common, flinging stars into interstellar chaos, igniting bursts of star formation, and feeding the supermassive black holes at their centers. Over time, the universe would grow increasingly violent as gravitational encounters disrupted the delicate balance of planetary systems, scattering worlds into cold intergalactic space or hurling them into their parent stars. As the contraction accelerated, the cosmic microwave background, the relic heat from the Big Bang, would no longer stretch to colder and colder wavelengths. Instead, it would compress, its wavelengths shortening, its temperature rising. The universe, once cooling toward thermal death, would begin to heat up again. This warming would be slow at first but inevitable, bathing the cosmos in a faint but steadily intensifying glow. The sky, already brightened by the influx of nearby galaxies, would now be filled with the hum of background radiation growing hotter and denser. Gravity would act as the great eraser of cosmic distances. Every cluster, every filament, every supercluster would eventually fall together. The Milky Way, Andromeda, and all the galaxies of the local group would merge into a single enormous elliptical galaxy. But even that would not survive forever. Larger and larger conglomerations would form, until the entire observable universe became one massive, bound object. As contraction progressed, the pace of events would quicken. The scale factor of the universe, the measure of its overall size, would shrink faster and faster. In the last stages, galaxies would merge into titanic, chaotic structures. The background radiation would rise to levels that could once again strip atoms of their electrons, turning the universe back into a glowing plasma. The era of stars and galaxies would end, replaced by a blinding, turbulent sea of energy and particles. In the final moments before the ultimate collapse, space itself would be so compressed that all matter and energy would be packed into a volume far smaller than the universe we know today. Temperatures would soar to unimaginable levels, densities would become infinite, and time itself might lose meaning. This catastrophic finale could mirror the conditions of the Big Bang, perhaps even leading to another cycle of expansion if certain cosmological models are correct. In that sense, the Big Crunch could be both an ending and a beginning, a cosmic heartbeat, where the death of one universe seeds the birth of another. If the universe's expansion were to halt, the balance of cosmic forces would dramatically shift over cosmic timescales, potentially paving the way for black holes to become the ruling entities of the cosmos. In today's ever-expanding universe, the growth of distance between galaxies generally works against the gravitational pull that tries to bring matter together. But without expansion pulling matter farther apart, gravity would have free rein to reorganize the universe's mass distribution. Stars, gas clouds, rogue planets, and even entire galaxies would no longer be drifting away from each other. Instead, they'd be on slow, inevitable paths toward dense gravitational wells, the regions where black holes reign. Black holes already play an important role in shaping cosmic evolution. At the centers of most galaxies sit supermassive black holes, some with masses billions of times that of our Sun, dictating the motion of stars in their vicinity. In a no-expansion scenario, these gravitational giants would become even more influential. Without cosmic expansion to dilute their reach, the effective volume in which their gravity dominates would expand over time. Stars from the galaxy's outskirts, previously moving away due to expansion, could eventually drift inward, their paths curved by the central black hole's pull. Over millions and billions of years, these infalling stars would either be swallowed directly or torn apart in spectacular tidal disruption events, adding to the black hole's mass and further strengthening its gravitational grip. The process wouldn't be limited to the centers of galaxies. Stellar mass black holes, remnants of massive stars, would also begin pulling in more material. In the current universe, these smaller black holes often remain isolated, with only occasional chances to consume matter. But in a stalled expansion cosmos, matter density would slowly increase in local regions as large-scale structures compress. Rogue planets, drifting through interstellar space, could eventually encounter these black holes and vanish into their event horizons. Gas clouds would be stripped apart and consumed, triggering bursts of X-ray radiation detectable across the cosmos. Over time, the distinction between different black holes might blur, as mergers between them become more frequent, producing gravitational wave events on a scale beyond anything possible in today's expanding universe. This black hole growth process would be relentless. Without expansion pulling everything apart, galaxy clusters themselves could collapse inward, their central black holes merging into colossal, ultra-massive black holes. These monsters could contain the mass of entire galaxies, their gravitational influence stretching light years in every direction. Matter falling toward them would be heated to extreme temperatures in accretion disks, radiating energy so intensely that entire regions of space could be lit up like cosmic beacons. Yet, despite these outbursts, the overall trajectory would be toward increasing darkness. Once the available matter was consumed, only the black holes would remain, slowly radiating away their mass over unimaginable timescales through Hawking radiation. In this scenario, black holes wouldn't just be dominant, they would be the only significant structures left. Stars would be gone, planets destroyed, and galaxies stripped of their luminous matter. The cosmic web would no longer be a network of light, but a graveyard of invisible, dense points scattered across space. The future universe could be thought of as a vast, cold arena populated by silent, isolated black holes drifting toward one another, merging when possible, and otherwise existing in lonely, lightless exile. Over trillions upon trillions of years, even these black holes would begin to evaporate, but until then, they would hold the title of cosmic monarchs, unmatched in their dominance. In a universe where expansion halts, one of the most fascinating possibilities lies in the potential for an ongoing stellar recycling loop, a cosmic cycle where star death and rebirth could continue for far longer than in our currently expanding cosmos. Today, the universe's accelerated expansion causes galaxies to drift apart, limiting the interaction between them and slowly starving regions of the gas and dust needed for new stars to form. But if expansion ceased, gravity would dominate more fully, and matter could be pulled back together in ways that revive the star-forming process again and again. When galaxies merge or collide, a process that would become increasingly common without expansion pushing them apart, vast clouds of gas are compressed, triggering intense bursts of star formation known as starbursts. These energetic events spawn thousands or even millions of new stars, including massive, short-lived giants that burn hot and fast. Once these stars exhaust their fuel, they die spectacularly, often in supernova explosions that enrich the surrounding space with heavy elements like carbon, oxygen, and iron, ingredients essential for building planets, complex molecules, and life itself. In an expanding universe, these starbursts eventually peter out as gas reservoirs are depleted and galaxies become isolated. But in a universe where expansion halts, the story doesn't end so neatly. The remnants of dead stars, white dwarfs, neutron stars, and black holes, remain gravitationally bound within galaxies or galactic clusters, and the gas ejected by supernovae doesn't simply drift away into an ever-expanding void. Instead, this material can be recycled, pulled together by gravity to form new molecular clouds, the cradles of future star formation. This cyclical process could extend the active, luminous life of the universe by trillions of years beyond current expectations. Instead of a slow fade into darkness, galaxies could repeatedly reignite new generations of stars as fresh gas is gathered from the intergalactic medium or funneled inward during mergers. This stellar recycling would create a dynamic cosmos that breathes and pulses on cosmic timescales, an ongoing dance of birth, death, and rebirth on a grand scale. Furthermore, the merging of galaxies and their central black holes in such a universe might stir up the interstellar medium, preventing gas from settling into stable configurations and instead promoting turbulent, star-forming environments. These interactions could even lead to the formation of massive star clusters and unusual stellar populations not commonly found in today's universe. While this prolonged star formation wouldn't last forever, gas would still be a finite resource. Halting expansion would delay the inevitable exhaustion of star-forming material. The universe would thus avoid a rapid decline into the cold, dark state associated with heat death, instead enjoying an extended period of cosmic vibrancy. The implications for life, if it persists that long, could be profound. With ongoing cycles of star birth and death, new habitable environments might continually arise, offering opportunities for life to develop and evolve across different epochs and locations. Civilizations far in the future could witness cosmic fireworks on a scale unimaginable to us now, as their skies blaze with newborn stars amidst the remnants of ancient stellar generations. This stellar recycling loop would transform the universe from a one-way march toward entropy into a more complex, cyclical system. Although the laws of thermodynamics would still apply, entropy would increase globally. The localized processes within galaxies could maintain pockets of order and energy flow, sustaining active astrophysical phenomena much longer than in a universe that keeps expanding. In this cosmic narrative, halted expansion breathes renewed life into the universe's stellar populations, extending the age of light and energy well beyond the slow fade we currently predict. It's a universe where the stars don't simply die and fade away but are born anew, cycling endlessly through the grand processes of creation and destruction that shape the cosmos. If the universe's expansion halted, the grand cosmic architecture that we know today, the vast web of galaxy clusters, filaments, and superclusters, would begin to transform in profound ways. Massive structures like the Virgo supercluster, which currently spans roughly 110 million light-years and contains thousands of galaxies including our own Milky Way, would no longer be pulled apart by the accelerating expansion of space. Instead, gravity would take the lead, slowly but relentlessly drawing these enormous assemblies together into ever larger structures. Currently, superclusters are the largest known bound structures in the universe, although they are still somewhat loosely held together. The accelerated expansion stretches the space between these superclusters, preventing them from merging into a single larger entity. But without expansion pushing galaxies and clusters apart, the gravitational pull within and between superclusters would dominate. Over unimaginable timescales, hundreds of billions to trillions of years, the individual galaxy clusters within a supercluster would move closer and closer. The Virgo supercluster's many clusters, including the local group and the massive Virgo cluster itself, would gradually converge. As these clusters merged, their constituent galaxies would also begin to collide and coalesce, creating colossal, sprawling galaxies that dwarf any we see today. The merging of these galaxies would produce massive elliptical galaxies, rich in stars but with little remaining cold gas for new star formation. The collisions would send stars careening on new orbits, creating tidal tails and streams visible as faint glows stretching far beyond the central galaxy. These galactic behemoths, sometimes called CD galaxies, could contain trillions of stars and extend over millions of light-years, shining as the dominant luminous entities within their merged superclusters. The sky from a planet orbiting a star within such a colossal galaxy would be breathtaking, filled with countless neighboring stars and perhaps visible remnants of past galactic collisions. Beyond individual galaxies, the combined gravitational forces of merging clusters and groups would deepen the gravitational potential wells of these superclusters. This would accelerate the infall of smaller galaxies and intergalactic gas, feeding further growth. The infalling matter might ignite new waves of star formation in pockets where gas remains, though most regions would become dominated by old stars and stellar remnants. The increased density and interaction rates would also heighten the frequency of supermassive black hole mergers. As the central black holes of merging galaxies spiraled inward, they would produce powerful gravitational waves, rippling across the cosmos and providing one of the few detectable signs of these slow but massive transformations. Eventually, superclusters like Virgo might become parts of even larger structures, mega-superclusters or cosmic islands, that consolidate huge portions of the visible universe. These conglomerates would be separated by vast, nearly empty voids, themselves expanding or remaining static depending on the broader cosmic conditions. Over trillions of years, this process would reduce the complexity of the cosmic web. Instead of billions of galaxies spread thinly across space, the universe would contain a relatively small number of gargantuan galaxies clustered into superstructures. The night sky for any civilization living in such a time would be filled with the light of these massive galactic giants, but the overall cosmic diversity would decline. Smaller, more delicate galaxies would be absorbed or destroyed, leaving behind a universe dominated by titanic, elliptical galaxies. In this way, the halting of expansion would mark the slow but steady end of the universe as a scattered collection of independent galaxies and clusters, reshaping it instead into a cosmos ruled by a few enormous galactic monarchs. This transformation would influence every aspect of cosmic evolution, from star formation to black hole growth to the distribution of matter on the grandest scales. If the universe's expansion halted, the grand cosmic architecture that we know today, the vast web of galaxy clusters, filaments, and superclusters, would begin to transform in profound ways. Massive structures like the Virgo supercluster, which currently spans roughly 110 million light-years and contains thousands of galaxies including our own Milky Way, would no longer be pulled apart by the accelerating expansion of space. Instead, gravity would take the lead, slowly but relentlessly drawing these enormous assemblies together into ever larger structures. Currently, superclusters are the largest known bound structures in the universe, although they are still somewhat loosely held together. The accelerated expansion stretches the space between these superclusters, preventing them from merging into a single larger entity. But without expansion pushing galaxies and clusters apart, the gravitational pull within and between superclusters would dominate. Over unimaginable timescales, hundreds of billions to trillions of years, the individual galaxy clusters within a supercluster would move closer and closer. The Virgo supercluster's many clusters, including the local group and the massive Virgo cluster itself, would gradually converge. As these clusters merged, their constituent galaxies would also begin to collide and coalesce, creating colossal, sprawling galaxies that dwarf any we see today. The merging of these galaxies would produce massive elliptical galaxies, rich in stars but with little remaining cold gas for new star formation. The collisions would send stars careening on new orbits, creating tidal tails and streams visible as faint glows stretching far beyond the central galaxy. These galactic behemoths, sometimes called CD galaxies, could contain trillions of stars and extend over millions of light-years, shining as the dominant luminous entities within their merged superclusters. The sky from a planet orbiting a star within such a colossal galaxy would be breathtaking, filled with countless neighboring stars and perhaps visible remnants of past galactic collisions. Beyond individual galaxies, the combined gravitational forces of merging clusters and groups would deepen the gravitational potential wells of these superclusters. This would accelerate the infall of smaller galaxies and intergalactic gas, feeding further growth. The infalling matter might ignite new waves of star formation in pockets where gas remains, though most regions would become dominated by old stars and stellar remnants. The increased density and interaction rates would also heighten the frequency of supermassive black hole mergers. As the central black holes of merging galaxies spiraled inward, they would produce powerful gravitational waves, rippling across the cosmos and providing one of the few detectable signs of these slow but massive transformations. Eventually, superclusters like Virgo might become parts of even larger structures, mega-superclusters or cosmic islands, that consolidate huge portions of the visible universe. These conglomerates would be separated by vast, nearly empty voids, themselves expanding or remaining static depending on the broader cosmic conditions. Over trillions of years, this process would reduce the complexity of the cosmic web. Instead of billions of galaxies spread thinly across space, the universe would contain a relatively small number of gargantuan galaxies clustered into superstructures. The night sky for any civilization living in such a time would be filled with the light of these massive galactic giants, but the overall cosmic diversity would decline. Smaller, more delicate galaxies would be absorbed or destroyed, leaving behind a universe dominated by titanic, elliptical galaxies. In this way, the halting of expansion would mark the slow but steady end of the universe as a scattered collection of independent galaxies and clusters, reshaping it instead into a cosmos ruled by a few enormous galactic monarchs. This transformation would influence every aspect of cosmic evolution, from star formation to black hole growth to the distribution of matter on the grandest scales. As these immense cosmic structures, superclusters and colossal galaxies, begin to merge and collide in a universe where expansion has ceased, the very temperature of the cosmos would experience significant shifts. Unlike the steady cooling we expect in an accelerating universe, where space itself stretches and energy dilutes over time, a halted expansion would create a different thermal environment, one that could periodically warm up as gravitational energy transforms into heat. When galaxies collide, it's not just a simple blending of stars and gas. It's a turbulent event filled with violent shocks and enormous energy releases. Clouds of gas slam into each other at thousands of kilometers per second, compressing and heating up dramatically. This process ignites bursts of star formation, starbursts, that flood their surroundings with intense ultraviolet and infrared radiation. These starbursts inject enormous amounts of energy into their galactic neighborhoods, heating the surrounding interstellar and intergalactic medium. On even larger scales, when entire galaxy clusters and superclusters merge, the effects become truly staggering. These colossal collisions generate shock waves in the hot, diffuse plasma that fills the space between galaxies, the intracluster medium. Temperatures in these regions can soar to tens or even hundreds of millions of degrees Kelvin, far hotter than the cores of most stars. The heat generated by these shocks creates bright X-ray emissions, which astronomers today detect as telltale signatures of ongoing cluster mergers. In a universe with no expansion to pull these structures apart, such mergers would become more common and more energetic over time. Instead of isolated events, clusters and superclusters would be locked in a gravitational dance, continuously colliding and combining. Each merger would release vast quantities of gravitational potential energy, converting it into kinetic and thermal energy, heating the intracluster gas and raising the average temperature of large cosmic regions. This warming would also affect the cosmic microwave background radiation, the ancient afterglow of the Big Bang that now bathes the universe at just under 3 Kelvin. Under normal expansion, the CMB gradually cools as space stretches. But with no expansion, the CMB temperature would stabilize, and the energy released by massive cosmic mergers could cause local temperature increases or fluctuations. The background radiation could experience temporary boosts in temperature, superimposed upon the otherwise steady glow. These temperature shifts would have cascading effects on cosmic evolution. Hotter intergalactic gas resists gravitational collapse because thermal pressure counteracts gravity. This means that while mergers might trigger bursts of star formation by compressing gas in some regions, in others the heated gas might remain too hot and diffuse to form new stars, temporarily suppressing star formation. The cycle of heating and cooling would create complex feedback loops, influencing how matter assembles on grand scales. Moreover, these elevated temperatures would affect the chemistry and ionization state of the intergalactic medium. Higher temperatures strip electrons from atoms, increasing the ionization fraction of gases between galaxies. This can alter how light travels through space, changing the opacity and spectrum of the universe in subtle ways. On extremely long timescales, as more mergers occur and the universe becomes dominated by larger, more massive structures, these temperature increases could become more widespread and persistent. The cosmos might experience phases of relative warmth punctuated by cooler periods as the gas cools and settles before being reheated by the next wave of collisions. Despite these heating events, the universe would not become uniformly hot like a furnace. Instead, temperature variations would be patchy and localized around dense regions where gravitational interactions are strongest. Vast voids between superclusters might remain cold and sparse, preserving pockets of chill in the cosmic landscape. In this scenario, the future universe's thermal history would be dynamic and uneven, a marked contrast to the monotonous cooling expected if expansion continues indefinitely. Instead of a simple fade to cold darkness, the cosmos would flicker with bursts of heat and light generated by the ceaseless dance of galaxies and clusters converging under gravity's unrelenting pull. This evolving thermal tapestry would also have important implications for the fate of matter and radiation. The interplay between heating from mergers and cooling from radiation would regulate the life cycle of stars, the growth of black holes, and the behavior of the intergalactic medium, creating a complex ecosystem governed by both chaos and order. The question of whether fundamental constants might change if the universe's expansion stopped, and the universe shifted into a dramatically different cosmic regime, is one that plunges us into the very heart of theoretical physics and cosmology. Our current understanding of the laws governing the cosmos relies on constants like the speed of light, the gravitational constant, Planck's constant, and the fine structure constant being truly constant, unchanging in time and space. But what if the grand cosmic environment itself altered so radically that these constants were no longer fixed? Could the cessation of expansion and the resulting cosmic conditions stress physics enough to cause subtle, or even profound, changes? At first glance, constants appear immutable. The speed of light, denoted by c, defines the ultimate speed limit of the universe. The gravitational constant, g, governs the strength of gravity. Planck's constant, h, sets the scale for quantum effects. These numbers are baked into our theories and underpin everything from atomic spectra to the evolution of stars. Yet, physicists have long pondered whether these constants are truly fundamental or emergent properties tied to the fabric of spacetime itself, and whether they might vary under extreme conditions. If the universe's expansion stopped, the large-scale dynamics of spacetime would be profoundly altered. The metric expansion of space, which stretches distances between galaxies and cools the cosmic microwave background, would give way to a more static or contracting cosmic backdrop. This would mean that the vacuum of space, the quantum vacuum full of virtual particles and fluctuations, might behave differently. Since many constants emerge from or relate to the vacuum's properties, changes in the vacuum state could ripple outward, influencing these fundamental values. One avenue where such effects might manifest involves the fine structure constant, alpha, which characterizes the strength of electromagnetic interactions. This dimensionless number, 1/137, determines how strongly charged particles interact via the electromagnetic force, affecting atomic structure, chemical reactions, and light emission. Some speculative theories suggest that alpha could vary with cosmic time or under different environmental conditions. If halted expansion changes the vacuum energy density, or the configuration of fields permeating space, it might subtly shift alpha's value. Even minuscule changes could have cascading effects on atomic and molecular behavior, potentially altering the chemistry that underpins everything from star formation to life. Similarly, the gravitational constant, g, might not be immune to such cosmic changes. Gravity is described by general relativity, a theory deeply intertwined with spacetime geometry. If spacetime geometry ceases to evolve via expansion and instead moves toward contraction or stasis, the effective strength of gravity might be modified. Some alternative gravity theories, like scalar tensor models, already propose that g can vary depending on the distribution of matter or the state of the universe. In a no-expansion scenario, the scalar fields that couple to gravity might settle into new configurations, changing gravitational behavior on both cosmic and local scales. This could alter everything from planetary orbits to the rate of galaxy mergers. Quantum constants like Planck's constant could also be affected, although such changes are far more speculative. Since H governs quantum phenomena, the very fabric of matter and energy at the smallest scales, even tiny shifts would have enormous consequences. Changes in quantum behavior could affect particle masses, decay rates, or the stability of atoms, potentially reshaping the physics that supports all matter. Beyond constants, the very laws of physics might experience shifts. Certain cosmological models suggest that fundamental symmetries, like Lorentz invariance, which states the laws of physics are the same regardless of velocity or orientation, could break down in extreme conditions. A halted or contracting universe might provide the extreme environment necessary for such symmetry breaking, opening doors to new physics beyond our current standard model and general relativity. This could lead to emergent phenomena, unknown forces, or altered particle interactions. Moreover, the role of dark energy itself is mysterious. The cosmological constant, often associated with dark energy, is a parameter tied closely to vacuum energy density. If expansion halts, this might imply dark energy behaves differently, possibly transitioning into a new phase or disappearing altogether. Such a shift would transform the vacuum state, and could indirectly affect fundamental constants. This is a realm where quantum field theory, cosmology, and particle physics intersect, and much remains speculative but tantalizing. Observationally, searches for time variation in constants like alpha and g have so far found no conclusive evidence for change, at least within the last several billion years. However, these observations come from a universe still expanding. If the universe were to enter a radically different phase, our current constraints might no longer apply, and new physics could emerge. From the perspective of advanced civilizations or future physicists billions of years hence, detecting and measuring changes in fundamental constants would provide profound insights into the evolution of the cosmos. Variations might manifest as shifts in spectral lines from distant stars, anomalies in gravitational behavior, or unexpected particle physics phenomena. Importantly, even subtle changes in constants could have significant implications for cosmic evolution. For example, if the electromagnetic force weakened slightly, stars might burn cooler and longer, altering stellar life cycles. If gravity strengthened, collapse processes like star formation and black hole mergers could accelerate, changing the rate at which cosmic structures evolve. These feedbacks would ripple throughout the cosmic ecosystem. Finally, this possibility challenges the very notion of constants. It suggests that the laws of physics, rather than being immutable, might be dynamic features woven into the evolving fabric of the universe, sensitive to the universe's large-scale behavior like expansion. If so, the halting of expansion is more than a cosmological milestone, it's a potential catalyst for a deeper transformation of the universe's fundamental nature. In summary, while we cannot say with certainty whether fundamental constants would change if the universe's expansion stopped, the scenario opens a Pandora's box of theoretical possibilities. It invites physicists to consider the universe not as a static backdrop with fixed rules, but as a dynamic entity whose very laws might evolve as cosmic conditions shift. This prospect underscores how intimately connected the fate of the universe is with the foundations of physics itself, a relationship still ripe with mysteries waiting to be unraveled. The discovery that the universe's expansion is accelerating was one of the most profound surprises in modern cosmology, fundamentally reshaping our understanding of the cosmos. This acceleration is attributed to a mysterious and poorly understood entity called dark energy, which currently makes up about 68% of the total energy content of the universe. Dark energy is thought to exert a repulsive force on the fabric of space, counteracting gravity and driving galaxies apart at an ever-increasing rate. But what if this acceleration suddenly halted? What if, instead of continuing to push galaxies farther apart, dark energy weakened, changed its nature, or even disappeared? Such a dramatic cosmic shift would force scientists to rethink everything about dark energy and its role in the universe. Dark energy's nature remains one of the greatest mysteries of physics. The simplest model treats it as a cosmological constant, a fixed energy density permeating all space evenly, exerting a constant negative pressure that drives expansion. In this view, dark energy is a fundamental property of the vacuum, unchanging and eternal. If expansion were to halt, this model would face immediate and profound challenges. A cessation of expansion implies that either the dark energy density decreased or that its repulsive effect was exactly balanced by gravity at some cosmic moment. Neither of these scenarios fits neatly into the cosmological constant picture. One possibility is that dark energy is not a fixed constant but a dynamic field, sometimes called quintessence, that evolves over time. In this framework, dark energy's strength could vary, fading or strengthening depending on underlying physical processes. If dark energy weakened enough for its repulsive effect to stop driving expansion, gravity would regain dominance, halting or even reversing expansion. Such a phase transition would revolutionize cosmology, revealing dark energy as a dynamic player rather than a static backdrop. The notion of dark energy undergoing a phase transition is more than theoretical musing. Some models suggest that dark energy could behave like a field trapped in a metastable state, a local minimum of a potential energy curve. Over cosmic timescales, the field might roll down to a lower energy state, altering its properties dramatically. This could cause dark energy to decrease in density, stop driving expansion, or even reverse into a contracting influence. Detecting such a transition would be like witnessing a cosmic metamorphosis, where the fundamental forces reshaping the universe suddenly change course. Alternatively, halting expansion might imply that dark energy interacts with matter or gravity in ways not previously understood. Modified gravity theories, such as F.R. gravity or scalar tensor models, propose that what we perceive as dark energy could be an emergent phenomenon arising from changes in gravity's behavior over large scales. In these scenarios, cosmic acceleration might be a transient phase caused by alterations in the laws of gravity rather than a permanent energy component. If expansion stopped, it could signal that these modifications evolved further, restoring gravity's dominance or reshaping cosmic dynamics entirely. Another intriguing possibility involves the concept of vacuum energy and its quantum nature. Quantum field theory predicts that empty space is not truly empty but filled with fluctuating fields and virtual particles, contributing to vacuum energy. The measured value of dark energy is famously small compared to naive quantum predictions, leading to the cosmological constant problem. If expansion halts, it might point toward unknown cancellations or interactions within vacuum energy, perhaps influenced by new physics or undiscovered fields that cause vacuum energy density to change over time or vanish altogether. Halting expansion would also impact the cosmic fate and necessitate reevaluations of the timeline and mechanisms by which the universe might evolve. Current dark energy models suggest a future dominated by accelerated expansion, leading to a cold, dilute cosmos where galaxies recede beyond observable horizons. If expansion stops, the universe's fate shifts dramatically, possibly toward collapse or a static state, and this calls for new theoretical frameworks that can account for such behavior. For observational cosmologists, a halt in expansion would trigger intense efforts to measure dark energy's properties more precisely. Instruments that survey distant supernovae, baryon acoustic oscillations, or the cosmic microwave background would search for subtle signs that dark energy's density or equation of state parameter, which relates pressure to energy density, is evolving. Any detected deviation from a pure cosmological constant would signal new physics and open the door to understanding dark energy as a dynamic field or interaction. Furthermore, a universe where expansion halts would demand explanations for why dark energy's effects changed at this particular cosmic epoch. Was this a predictable evolution, a random fluctuation, or evidence of deeper physical laws governing cosmic energy components? This raises profound questions about fine-tuning and cosmic coincidence. Why would dark energy's strength diminish just as the universe reached a certain size or age? Could this be a hint toward a multiverse or anthropic reasoning, where our observable universe is just one realization among many, each with different dark energy histories? Theoretically, halting expansion might inspire new models incorporating interactions between dark energy and dark matter, the elusive form of matter that shapes galaxies and clusters but does not emit light. Such interactions could modify the effective strength of dark energy over time, potentially leading to a balance point where expansion stops. This coupling could create feedback mechanisms that regulate cosmic acceleration, introducing oscillations or cyclic phases in the universe's expansion history. In summary, if the universe's expansion were to stop, it would force a seismic rethink of dark energy theories. The simplest cosmological constant model would be challenged or overturned, replaced by dynamic field models, modified gravity theories, or entirely new physics describing vacuum energy and cosmic evolution. Understanding why expansion halts, and what happens next, would become a central quest in cosmology, driving new observations, experiments, and theoretical breakthroughs. Ultimately, halting expansion would not be just a change in cosmic scale, but a fundamental shift in how we understand the universe's most mysterious component. It would signal that dark energy is not a passive backdrop but an active, evolving force with a story still unfolding, a story that could redefine the destiny of everything we know. The question of whether the universe's expansion could actually stop is one that lies at the very frontier of cosmology, touching on observations, theoretical models, and the fundamental physics that govern spacetime. To assess the possibility that expansion might halt, we must consider both what current data tell us about the universe's acceleration and what theoretical frameworks allow or forbid such a cosmic event. Since the late 1990s, observations of distant Type I supernovae revealed a startling truth. Not only is the universe expanding, but this expansion is accelerating. This discovery, awarded the Nobel Prize in Physics in 2011, shifted the cosmological paradigm from a slowing or steady expansion to one driven by a mysterious dark energy. These supernova measurements were bolstered by detailed studies of the cosmic microwave background radiation by missions like WMAP and Planck, as well as galaxy surveys mapping large-scale structures and baryon acoustic oscillations. Collectively, these datasets establish a consistent picture. The universe's expansion rate, quantified by the Hubble parameter, is increasing over time, implying repulsive effects from dark energy dominate cosmic dynamics. In the standard lambda-cold dark matter model, the prevailing cosmological framework, dark energy is modeled as a cosmological constant, lambda, a fixed vacuum energy density with negative pressure that remains constant throughout cosmic history. In this scenario, expansion continues indefinitely, accelerating ever faster as matter density dilutes due to expansion. Under lambda-cold dark matter, the expansion cannot stop. It asymptotically approaches an exponential de Sitter phase, where galaxies recede at speeds surpassing the speed of light relative to each other, and distant cosmic structures disappear beyond event horizons. However, this model, while remarkably successful in fitting observations, is not the final word on cosmology. It leaves many puzzles unsolved, notably the nature of dark energy itself. Given this uncertainty, alternative models have been proposed that could, in principle, allow for scenarios where expansion slows, halts, or even reverses. One such class involves dynamic dark energy models, where the energy density changes with time. Quintessence, for instance, treats dark energy as a scalar field slowly evolving in a potential landscape. Depending on the field's dynamics, its energy density and pressure can vary, possibly decreasing or even becoming negative. If the dark energy density diminishes enough or flips sign, the repulsive effect driving expansion might weaken or vanish. This opens the door for expansion to slow or stop, potentially transitioning to contraction if gravity regains dominance. Another possibility arises in modified gravity theories. Instead of dark energy being a substance or field, cosmic acceleration could emerge from changes to general relativity on large scales. Theories like F.R. gravity or brane-world models modified the equations governing gravity, leading to different expansion histories. In these frameworks, the acceleration phase might be transient, a feature of certain epochs rather than a permanent condition. If the modifications evolve or switch off, the expansion rate could change dramatically, including the possibility of halting. Observationally, distinguishing these scenarios is challenging. Current measurements of the equation of state parameter W, the ratio of dark energy's pressure to its energy density, hover near -1, consistent with a cosmological constant. Small deviations are allowed but tightly constrained. Upcoming surveys like the Vera Rubin Observatory's LSSD, Euclid, and the Nancy Grace Roman Space Telescope aim to measure W with unprecedented precision, potentially detecting evolution that hints at dynamic dark energy or modified gravity. Yet, even if current data suggests continuing acceleration, it remains difficult to categorically exclude a future halt in expansion. Cosmology is inherently extrapolative. We observe the universe as it is now or in the relatively recent past and model its future based on known physics. But unknown physics could emerge, changing the cosmic trajectory. For instance, a phase transition in dark energy, akin to water freezing or boiling, might occur billions or trillions of years from now, altering expansion. From a theoretical perspective, the ultimate fate of the universe depends on the balance of energy components. The Friedmann equations, which govern cosmic expansion, relate the expansion rate to matter density, radiation, curvature, and dark energy. If dark energy weakens or reverses sign, the decelerating influence of matter and radiation could stop expansion. The universe might reach a turnaround point, where the scale factor's growth halts before contracting. However, current cosmological parameters indicate the universe is spatially flat or nearly so, and matter density is insufficient to cause recollapse under the cosmological constant assumption. This suggests that, absent changes in dark energy or gravity, halting expansion is unlikely. But if dark energy evolves or new physics alters gravity, spatial curvature or effective energy densities might change, permitting expansion to stop. Another factor is the nature of dark energy's equation of state. If W-1, a so-called phantom energy, expansion would not just continue but accelerate toward a big rip, or even atoms are torn apart. If W-1 but still less than -1/3, accelerated expansion occurs, but changes in W over time could shift expansion dynamics. Tracking W's evolution is thus critical to understanding if expansion could halt. Cosmologists also consider cyclic or bouncing models, where expansion and contraction phases alternate indefinitely. These models naturally incorporate expansion halting and reversing, avoiding singular beginnings or endings. While such models face challenges explaining current observations, they remain intriguing possibilities. In summary, while the best current data and the lambda-cold dark matter model predict eternal acceleration and no halt, fundamental uncertainties about dark energy and gravity leave room for alternative cosmic futures. A halted expansion is not ruled out but would require dark energy's properties to evolve or modifications to gravity beyond general relativity. The possibility that expansion could stop challenges us to keep probing the cosmos with ever more precise observations and to develop richer theoretical frameworks. It underscores the humility needed in cosmology. Our universe's future remains an open question, bound to mysteries waiting to be unraveled by science and imagination. Beyond the conventional cosmological models, several intriguing alternative explanations have been proposed by physicists to account for a scenario where the universe's expansion might halt, or even reverse. These ideas push the boundaries of current understanding and explore how subtle changes in the nature of dark energy, or gravity itself, could profoundly reshape cosmic evolution. Central to many of these theories are concepts like phase transitions in dark energy and modifications to gravitational physics, mechanisms that could transform the universe's fate from endless acceleration to a more complex or cyclical destiny. One of the most compelling alternative explanations involves phase transitions in dark energy. Drawing an analogy to familiar phase changes, like water freezing into ice or boiling into steam, this idea suggests that dark energy might not be a fixed entity, but a dynamic substance capable of shifting between different states. In such a picture, the vacuum energy that permeates space could settle into different energy levels depending on underlying physical conditions, much like how water's physical state depends on temperature and pressure. If dark energy currently resides in a false vacuum, a metastable state with higher energy, it could eventually decay to a true vacuum, with lower energy density. Such a transition would drastically alter the universe's expansion. The repulsive force driving acceleration could weaken, stop, or even reverse, allowing gravity to regain dominance and halt expansion. This cosmic phase transition would act like a switch, changing the universe's large-scale dynamics and setting it on a new evolutionary path. models exploring vacuum metastability are grounded in quantum field theory and string theory landscapes, where multiple vacuum states with different energy densities are possible. These models also connect with ideas about the early universe's inflationary phase, which itself was driven by a vacuum-like energy that ended via a phase transition, leading to the hot Big Bang. If dark energy behaves similarly on vastly larger timescales, future phase transitions could reshape the cosmos. Such transitions might not be instantaneous but could spread like a bubble expanding at near light speed, transforming regions of space and leaving detectable signatures. Some theorists speculate that these transitions might be accompanied by bursts of high-energy particles or gravitational waves, offering potential observational windows into this profound process. In parallel with phase transitions, physicists also investigate modifications to gravity as a route to halting expansion. While general relativity has passed stringent tests in the solar system and strong gravity regimes, its extrapolation to cosmic scales remains open to challenge. Modified gravity theories alter Einstein's equations or introduce new fields, leading to different predictions about how the universe expands. One prominent class of models is F-R gravity, where the Einstein-Hilbert action is generalized by replacing the Ricci scalar R with a function f(r). These modifications can produce late-time acceleration without invoking dark energy, or change the effective strength of gravity over large scales. Depending on the form of f(r), cosmic acceleration might be a transient phase, with expansions slowing or halting as the function's form evolves. Other models involve scalar tensor theories, which introduce additional scalar fields coupled to gravity. These scalar fields can mediate a dynamic gravitational constant, influencing expansion rates. Through mechanisms like the chameleon effect, these fields can evade local gravity tests while altering cosmic expansion, possibly causing the universe's growth to stop or reverse. Some frameworks consider brane-world scenarios, inspired by string theory, where our four-dimensional universe is a brane, embedded in higher-dimensional space. Interactions with extra dimensions can modify gravity's behavior, leading to complex expansion histories that include halting or cyclic phases. In addition, the concept of interacting dark energy and dark matter has gained attention. If these two dark components exchange energy or momentum, the effective dark energy density can evolve in non-trivial ways, potentially slowing or stopping expansion. Such coupling might arise naturally in particle physics extensions beyond the standard model and could have observational consequences detectable through galaxy clustering and cosmic microwave background anisotropies. Other speculative ideas involve emergent gravity, where gravity is not a fundamental force but emerges from underlying quantum or thermodynamic principles. In these views, cosmic acceleration and expansion dynamics might arise from statistical properties of microscopic degrees of freedom. Changes in these emergent properties could lead to transitions in expansion behavior. Lastly, cyclic or bouncing universe models offer radical alternatives where the universe undergoes infinite sequences of expansion and contraction. In such cosmologies, expansion halts at a maximum size before reversing into a contraction phase, potentially culminating in a big crunch, or rebirth into a new expansion cycle. These ideas resonate with some interpretations of quantum cosmology and offer ways to avoid singularities and explain cosmic initial conditions. Each of these alternative scenarios challenges the simple picture of eternal acceleration and introduces rich new dynamics for the cosmos. They provide fertile ground for theoretical exploration and motivate a host of observational tests aimed at detecting deviations from lambda-cold dark matter predictions. However, all these ideas face significant hurdles. They must fit the extremely precise data from supernovae, cosmic microwave background, large-scale structure, and gravitational lensing surveys. They must also avoid conflicts with local gravity tests and remain consistent with high-energy physics constraints. Nonetheless, the possibility that the universe's expansion might halt compels scientists to consider these alternative explanations seriously. The stakes are high. Understanding the true nature of dark energy and gravity could revolutionize physics, reshape our view of cosmic destiny, and illuminate the deepest workings of the universe. If the universe's expansion were to halt, shifting from the accelerating growth we observe today into a cosmic standstill, or even contraction. The implications for life, particularly for civilizations billions of years in the future, would be profound and far-reaching. While it's difficult to predict specifics across such vast timescales, we can explore how the changing cosmic environment might influence the conditions that support life, the evolution of intelligent beings, and the potential trajectories of civilizations facing an altered universe. First, it's important to understand the fundamental cosmic factors that shape the prospects for life: the availability of energy, the stability of planetary systems, the formation and destruction of stars, and the broader galactic environment. These factors are tightly linked to the universe's expansion history, since expansion affects the distribution and dynamics of matter, the temperature of the cosmic background, and the evolution of galaxies and stars. In a universe where expansion halts, the large-scale structure of space would evolve differently from the infinite acceleration scenario. Instead of galaxies receding forever into darkness beyond event horizons, they would remain within gravitational reach. Over immense timescales, galaxies and clusters could move closer, merge, and interact more frequently. This dynamic cosmic neighborhood would create both opportunities and challenges for life. One immediate consequence would be an increase in the frequency of galactic mergers and collisions, as gravity gains the upper hand over cosmic expansion. From a civilization's viewpoint, residing in a galaxy on a collision course might be a double-edged sword. On the positive side, galactic interactions often trigger bursts of star formation, starbursts, that can enrich the galaxy with fresh material, including heavy elements essential for building rocky planets and complex chemistry. These stellar nurseries could provide new generations of stars with habitable zones where life might arise. However, the violent nature of galaxy collisions also brings hazards. The intense gravitational perturbations could destabilize stellar orbits, increasing the likelihood of catastrophic events like close stellar flybys or ejections. Massive radiation from active galactic nuclei, powered by feeding supermassive black holes, and supernovae triggered by starbursts could bathe nearby systems in harmful high-energy particles, challenging the survival of delicate biospheres. Over billions of years, such an environment might require civilizations to develop sophisticated strategies for survival, relocating within their galaxies, shielding themselves from radiation, or even migrating to safer galaxies if technology permits. The expanding horizons of space travel could become a necessity, not a luxury. Another key factor is the temperature of the cosmic microwave background, CMB, the faint afterglow of the Big Bang. In an eternally expanding universe, the CMB cools progressively, approaching absolute zero over unimaginable timescales. A colder universe means less background radiation, which helps in dissipating waste heat from living systems and technological devices, critical for thermodynamic efficiency. If expansion halts, however, the CMB temperature would stabilize and remain higher than it would otherwise be. This residual heat bath imposes a fundamental thermodynamic limit on energy extraction and computation, potentially constraining the longevity and efficiency of life and civilizations. On the other hand, the increased interactions and mergers among galaxies could temporarily raise local background temperatures through heating of intergalactic gas, as previously discussed. These temperature shifts might create fluctuating conditions where biospheres must adapt to varying radiation environments. In terms of stellar evolution, a halted expansion could lead to more frequent mergers and collisions among stars and star clusters, generating energetic phenomena like supernovae and gamma-ray bursts. These events pose significant risks to life by exposing planets to intense radiation. Civilizations in such environments would likely need to develop advanced protective measures or relocate to more stable regions. Yet, the clustering of galaxies and stars could also facilitate the exchange of materials and life-bearing compounds between star systems, through processes like stellar winds, cometary transfer, or even intentional panspermia by intelligent beings. This closer cosmic proximity might enhance the spread and diversification of life across the universe. On extremely long timescales, star formation would gradually decline as gas reservoirs are consumed or heated, but without expansion, gas might be retained more effectively within clusters, potentially prolonging star formation compared to an accelerating universe where gas escapes into expanding voids. This extended star formation period offers a longer window for life to emerge and evolve. Black holes, predicted to dominate the universe in the far future, could serve as exotic energy sources for advanced civilizations. Theoretical concepts like Hawking radiation or energy extraction via accretion disks might be harnessed, enabling life to persist even as ordinary stars fade. A static or contracting universe might facilitate the collection and utilization of such energy reservoirs as matter becomes more concentrated. From a philosophical perspective, the halt in cosmic expansion challenges humanity's understanding of its place in the cosmos. Our current perspective is rooted in a universe expanding toward eventual isolation and cold death, a narrative of inevitable decline. A halting or contracting universe introduces a more complex story, one where cosmic renewal or collapse might occur, where endings and beginnings intertwine, and where life's resilience is tested in new ways. Civilizations billions of years in the future, if they survive, would likely have developed technologies far beyond our current imagination. They might engineer their cosmic environment, stabilizing stellar neighborhoods, manipulating gravity, or even influencing dark energy itself to shape their destiny. Concepts from speculative fields like Dyson spheres, interstellar migration, or cosmic engineering take on new urgency and feasibility in a universe where expansion is no longer a given. Additionally, a halted expansion could influence the arrow of time as perceived by life forms. With cosmic time and energy fluxes altered, notions of causality, aging, and evolution might differ fundamentally from our current experience. This raises profound questions about consciousness, survival, and the meaning of existence in a changing cosmos. Finally, the psychological and cultural impact on civilizations aware of a changing universe cannot be overstated. Knowing that cosmic expansion, the backdrop for billions of years of evolution, is stopping might inspire new philosophies, myths, and scientific quests. Life might adapt not only biologically but culturally and intellectually to a universe in flux. In conclusion, while a halt in the universe's expansion would present significant challenges for life and civilizations billions of years in the future, it would also open new possibilities. The dynamic cosmic environment could foster rich evolutionary paths, advanced technologies, and novel modes of existence. Far from a static or doomed scenario, a halted expansion invites us to imagine a cosmos where life's story is intertwined with the grandest transformations of space and time, underscoring the deep connection between life and the universe itself. To live in a universe that is still expanding, and accelerating at that, is to inhabit a cosmos in motion, one whose vastness is continuously unfolding before us. This reality, shaped by discoveries made over the past century, profoundly influences our understanding of existence, our place in the grand cosmic tapestry, and even the philosophical and existential questions that have long captivated humanity. Reflecting on what it means to live in such a dynamic universe connects the distant future with our present moment, grounding our awareness in a cosmic story that is still being written. For most of human history, the night sky appeared fixed and eternal. Stars and galaxies seemed like unchanging fixtures, a stable backdrop against which the dramas of human life played out. It was only in the 20th century, with advances in astronomy and physics, that we learned the universe is anything but static. Edwin Hubble's observations in the 1920s revealed that distant galaxies are receding from us, implying that space itself is expanding. Later, the discovery that this expansion is speeding up, driven by an enigmatic dark energy, deepened the mystery and transformed cosmology into a profoundly dynamic science. To live in this expanding universe is to be participants in an unfolding cosmic evolution. We are not observers of a fixed stage but inhabitants of a growing, changing arena where distances stretch, galaxies drift apart, and cosmic structures evolve over billions of years. This expansion shapes everything from the formation of galaxies and stars to the background radiation that bathes the cosmos. It also sets limits on what we can observe, as some galaxies move away faster than light due to expansion, slipping beyond our cosmic horizon and forever lost to our view. Philosophically, the expanding universe challenges our notions of permanence and stability. It reminds us that change is fundamental at the grandest scales, that nothing is truly eternal or fixed. This cosmic impermanence parallels many human experiences and invites reflection on the transient nature of existence itself. Our lives, cultures, and even civilizations are but brief flickers within the immense timescales of cosmic history. Yet, the universe's expansion also inspires awe and wonder. The fact that the cosmos has been expanding and evolving for 13.8 billion years connects us to a vast continuum stretching from the Big Bang to the distant future. It frames our story as part of a larger process, one marked by creation, growth, transformation, and eventual fate. In this light, humanity's quest for knowledge, exploration, and meaning gains a cosmic context, fueling scientific curiosity and philosophical contemplation. On a practical level, living in an expanding universe influences how we interpret astronomical observations and understand the cosmos' structure. The redshift of galaxies, the stretching of light waves as space expands, allows astronomers to measure distances and map the universe's growth. The cosmic microwave background radiation, a relic of the early universe, serves as a snapshot of the cosmos' infancy, revealing conditions shortly after the Big Bang. These tools and insights hinge on the fact that expansion is ongoing. Moreover, the accelerating expansion hints at a future where distant galaxies vanish from view, leaving behind an increasingly isolated local group of galaxies. This prospect shapes theories about the long-term future of the cosmos and the eventual heat death scenario, where stars burn out and the universe cools to near absolute zero. Living in the present, we are witnessing a unique epoch, one in which the universe is transparent, rich with galaxies and cosmic phenomena visible to us. Future observers, billions of years hence, might see a vastly different cosmos. From a human perspective, this awareness invites humility and awe. We are tiny actors on a pale blue dot suspended in an expanding sea of space and time. Our cosmic epoch is a fleeting window into the universe's grand evolution. This realization can inspire a sense of stewardship for our planet and a yearning to understand our origins and destiny within this unfolding story. The expanding universe also poses profound existential questions. If the cosmos is growing ever larger, what does that imply about the meaning and permanence of life and civilization? Does expansion reflect a cosmic tendency toward isolation and entropy? Or is it part of a larger cycle or process yet to be understood? These questions bridge science, philosophy, and spirituality, touching on themes of creation, impermanence, and hope. In cultural terms, the expanding universe has influenced art, literature, and popular imagination. It provides a canvas for storytelling about cosmic voyages, the search for extraterrestrial life, and humanity's future among the stars. Science fiction, in particular, explores the implications of a universe in flux, imagining futures shaped by cosmic expansion or its hypothetical halting. Scientific advancements continue to deepen our understanding of expansion. Precision measurements of cosmic parameters, large-scale surveys mapping dark energy's influence, and theoretical work probing the universe's fundamental nature push the boundaries of knowledge. Each discovery reshapes our cosmic perspective and enriches the human narrative. At a more personal level, knowing we live in an expanding universe can influence how individuals perceive time and space. The vastness and dynamism of the cosmos may evoke feelings of insignificance but also connectedness to the past, present, and future of everything that exists. This duality can be both humbling and empowering, motivating a search for meaning in a universe that is constantly growing and changing. Furthermore, the expanding universe sets the stage for humanity's future exploration and potential colonization of space. Understanding cosmic expansion informs strategies for interstellar travel, communication, and survival in a universe where distances between galaxies increase relentlessly. It frames the challenges and opportunities facing future generations venturing beyond our solar system. From a scientific philosophy viewpoint, the expanding universe exemplifies the power of human inquiry and observation. The realization that space itself stretches, altering how we perceive distance and time, reveals the deep interplay between measurement, theory, and the nature of reality. It underscores the provisional nature of scientific knowledge and the ongoing quest to grasp the cosmos's true workings. living in an expanding universe also raises questions about fate and free will on cosmic scales. While physical laws govern expansion, the emergence of conscious beings capable of understanding and perhaps influencing cosmic phenomena introduces complexity. Could advanced civilizations one day manipulate dark energy or cosmic expansion? Such ideas remain speculative but challenge us to consider the interplay between destiny and agency in a dynamic cosmos. The expansion also influences cosmological horizons, the limits beyond which information cannot reach us. These horizons impose fundamental boundaries on what can be known and observed, shaping the very fabric of scientific knowledge and experience. A universe still expanding means these horizons grow, isolating regions of space and restricting communication over extreme distances. In the context of existential risk, the expanding universe informs scenarios for long-term survival. It suggests eventual isolation and cooling, guiding considerations for energy use, resource management, and the sustainability of life and civilization over cosmic timescales. This awareness frames both cautionary and hopeful perspectives on humanity's future. Finally, the expanding universe invites a sense of wonder and mystery. Despite tremendous progress, fundamental questions remain. Why does dark energy exist? What is its true nature? How will expansion evolve? These mysteries drive scientific exploration and fuel the human spirit's quest to comprehend the infinite. In essence, living in a universe that is still expanding situates humanity within a grand, unfolding cosmic drama. It connects our present moment to billions of years of history and unimaginable future epochs. It challenges us to reconcile our fleeting existence with the vast, dynamic cosmos, a cosmos whose expansion shapes everything we observe, experience, and strive to understand. Our place in this expanding universe is both fragile and remarkable. It is a story of growth and change, of discovery and mystery, of endings and beginnings intertwined. Embracing this perspective enriches our appreciation of the cosmos and deepens the meaning we find in life, science, and the shared journey of existence. The universe, when viewed through the lens of human storytelling, unfolds as an epic saga of birth, growth, transformation, and eventual fate, an unfolding narrative spanning billions of years, filled with moments of grandeur, mystery, and unexpected turns. To frame the halting of cosmic expansion as a plot twist in this vast cosmic story is to imagine a dramatic and profound moment when the familiar arc of the universe suddenly shifts, rewriting its destiny and challenging the assumptions woven into our understanding of existence. From the very beginning, the universe's tale is one of expansion, a rapid inflationary burst, followed by a slower but persistent growth stretching space itself. This opening chapter, the Big Bang and its immediate aftermath, sets the stage for everything that follows: the formation of atoms, stars, galaxies, and eventually planets and life. The expansion is the backdrop, the canvas upon which the cosmic drama is painted, giving the story its rhythm and scope. For billions of years, this expansion drives the narrative forward, carrying galaxies apart, allowing structures to emerge and evolve, and cooling the cosmic environment to the temperatures that permit complexity. The plot thickens as dark energy emerges, accelerating expansion and reshaping the universe's trajectory. This acceleration introduces tension and uncertainty, suggesting a future where cosmic isolation and entropy reign supreme, a slow fading into darkness and cold. But what if the story takes an unexpected turn? Imagine that, just as we believe the expansion will continue forever, it halts. This sudden cosmic pause is a plot twist, a moment when the universe's trajectory bends, disrupting the anticipated climax and opening new narrative possibilities. In storytelling terms, it's the unexpected twist that forces characters to reevaluate their fate and adapt to a changed reality. This halting of expansion reshapes the cosmic stage. The galaxies, no longer forced apart by accelerating space, begin to interact more closely, forming new alliances and conflicts, mergers, collisions, and gravitational dances that alter the cosmic landscape. The plot thickens with the emergence of new phenomena, a resurgence of cosmic drama that had seemed destined to fade into silence. From the perspective of life and civilization scattered across the cosmos, this twist brings both hope and challenge. The possibility of renewed star formation, energetic interactions, and closer cosmic neighbors suggests new chapters of opportunity. Yet the increased violence and instability also introduce peril, forcing cosmic protagonists to innovate, survive, and perhaps even shape their destiny amid changing conditions. This narrative shift also introduces philosophical complexity. The cosmic story is no longer a simple arc toward inevitable heat-death but a layered tale with cycles, reversals, and transformations. It evokes themes of renewal and collapse, of resilience and fragility, of beginnings that emerge from apparent endings. In this way, the universe's halted expansion becomes a metaphor for the unpredictability and richness of existence itself. In storytelling, a plot twist invites reflection on causality and meaning. What caused the expansion to stop? Is it a natural evolution of cosmic forces, an external intervention, or the result of deeper physical laws yet undiscovered? These questions parallel those faced by characters confronting unexpected events, seeking understanding and control in a changing world. Moreover, the halted expansion forces a reconsideration of cosmic destiny. The story's ending, once thought fixed, now branches into new possibilities, a stable, static universe, a slow contraction leading to a big crunch, or a complex, oscillating cycle of expansions and contractions. Each path offers a different narrative tone, tragic, hopeful, or enigmatic, inviting us to ponder the ultimate meaning of the cosmos. This cosmic plot twist also challenges the role of observers within the story. Human beings, with their capacity for curiosity, creativity, and reflection, become not only characters in the narrative but also narrators, interpreting, predicting, and perhaps influencing the unfolding drama. The halted expansion reframes their quest for knowledge, intensifying the urgency and significance of understanding cosmic forces. In the broader cultural imagination, such a twist resonates with timeless themes found in myths, literature, and philosophy: the sudden reversal of fortune, the collapse and rebirth of worlds, the dance between order and chaos. It echoes motifs of the phoenix rising, the cyclical nature of time, and the profound interplay between fate and free will. From a scientific perspective, the plot twist of halted expansion sparks renewed exploration and discovery. It compels researchers to develop new theories, design innovative experiments, and seek deeper insights into dark energy, gravity, and the fundamental fabric of reality. The narrative becomes a journey of intellectual adventure, with mystery and revelation intertwined. At a metaphysical level, the halted expansion invites contemplation of the universe as a living story, one that evolves, surprises, and invites participation. It challenges us to see existence not as a static fact but as an ongoing process shaped by forces both known and unknown, with each twist revealing new layers of meaning. This reframing also impacts our sense of time. The linear progression of cosmic history gives way to a more complex temporal structure, where beginnings and endings intertwine, and the future is an open field of potentialities. The halted expansion is a moment where the narrative pauses, allowing for reflection, transformation, and new directions. In practical terms, imagining the universe's halted expansion as a story encourages interdisciplinary dialogue between cosmologists, philosophers, artists, and thinkers, each contributing perspectives that enrich the cosmic narrative. It bridges the gap between empirical science and human meaning-making, underscoring that the universe's story is both a physical reality and a human experience. Furthermore, this plot twist invites us to reconsider our own stories. Just as the universe can change course, so too can human lives and civilizations adapt, transform, and find new paths amid uncertainty. The halted expansion becomes a cosmic metaphor for resilience, adaptability, and the power of change. In this grand narrative, the universe is not a fixed script but a living epic, one where endings are beginnings, pauses are preludes, and every moment holds the potential for surprise. The halting of expansion is the dramatic pivot, the unforeseen chapter that redefines everything that came before and everything yet to come. By embracing this view, we align ourselves with the cosmos not as passive spectators but as participants in an unfolding story, a story that challenges, inspires, and connects us across space and time. The halted expansion is the turning point, the cosmic plot twist that invites wonder, inquiry, and the deepest reflections on existence. Imagine for a moment standing at the edge of cosmic time, peering into the vast expanse of the universe's future. You watch as the fabric of space stretches outward relentlessly, galaxies drifting apart faster and faster, the cosmic web thinning, the sky growing darker and emptier. Now, envision an unexpected event, a sudden halt to this expansion, a cosmic pause that defies the story we thought we knew. The question that emerges is both profound and paradoxical. Would stopping the universe's expansion save it, or doom it faster? This thought experiment invites us to wrestle with the deepest mysteries of cosmology, thermodynamics, and the fate of life and matter in the cosmos. It challenges our intuition, forces us to examine the delicate balances and tensions underlying everything we observe, and confronts us with the uncertain destiny of all existence. To grapple with this question, we must consider the implications of halted expansion from multiple angles: the physical, the biological, the thermodynamic, and the philosophical, and how these layers intertwine in shaping cosmic outcomes. First, consider what saving the universe might mean. Does it imply preserving conditions favorable for life and complexity over the longest possible timescale? Does it mean preventing catastrophic collapse or cosmic destruction? Or is it about maintaining a universe rich in structure, energy, and possibility, resisting decay and entropy for as long as possible? The answer depends on what aspects of the universe's fate we prioritize, and on the interplay of cosmic forces and processes. If expansion stops, the immediate consequence is a dramatic shift in the balance between repulsive and attractive forces in the universe. The outward push of dark energy, which currently drives acceleration, would cease to separate galaxies at increasing speeds. Gravity, the cosmic sculptor, would begin to assert greater influence, potentially drawing galaxies and clusters back together. This shift opens the door to scenarios where cosmic structures grow denser, interactions become more frequent, and the universe's large-scale dynamics reverse or stabilize. From one perspective, this halt could save the universe from the isolation and desolation anticipated in an eternally accelerating cosmos. Currently, accelerated expansion predicts a big freeze, or heat death. Galaxies recede beyond observational horizons, star formation dwindles, and the universe approaches thermodynamic equilibrium at near absolute zero. Over unimaginable time, energy gradients flatten, entropy maximizes, and all activity ceases. Life, if it survives at all, faces a bleak and lonely fate. Stopping expansion could delay or avert this fate. Without galaxies drifting irreversibly apart, the supply of gas for star formation might persist longer within gravitationally bound structures. Mergers and collisions could trigger renewed bursts of star birth, extending epochs of cosmic vitality. The cosmic microwave background's temperature might stabilize rather than decline, providing a consistent thermal environment that affects the thermodynamic constraints on life and energy use. In this sense, halting expansion could prolong the universe's phase of complexity and activity. More material recycling through stellar death and rebirth, increased galaxy interactions, and concentrated matter might foster conditions where life persists and evolves over longer spans. The universe would remain a dynamic, interacting arena instead of an ever-thinning expanse. Yet there is a flip side. The gravitational pull regained after halted expansion might set the universe on a path toward contraction, a reversal of its long expansionary history. This would lead to the so-called Big Crunch, a scenario where matter and energy collapse inward, densities and temperatures rise, and the universe shrinks back toward a highly energetic and compact state. From this vantage point, stopping expansion could actually doom the universe faster than eternal acceleration. Instead of a slow fade into cold and silence, the cosmos might face a catastrophic implosion, ending in extreme conditions that obliterate structure and complexity. The environment would become increasingly hostile, marked by intense radiation, gravitational turbulence, and eventual singularity. The Big Crunch is often portrayed as a dramatic, terminal event, an ultimate cosmic collapse where space-time itself terminates or transitions. While some theories propose bounce models or cyclic universes where such a collapse leads to rebirth, the immediate effect would be an end to all known structures and life as we understand them. This duality, where halted expansion can be seen as both salvation and doom, reveals the profound uncertainty and delicacy of cosmic fate. The universe's trajectory hinges on the precise balance of forces, the nature of dark energy, and the fundamental laws governing matter and space-time. Another dimension to consider is thermodynamics. The second law dictates that entropy, a measure of disorder, tends to increase over time, driving the universe toward equilibrium and heat death. In an accelerating universe, entropy increases as matter dilutes and energy gradients flatten. Halting expansion changes the thermodynamic landscape. Gravitational clustering might concentrate matter, creating pockets of lower entropy and energy gradients that sustain processes. However, increased clustering and collisions also generate heat and radiation, which contribute to entropy. The eventual fate depends on whether these processes can sustain complexity longer than expansion-driven cooling allows, or if gravitational collapse accelerates entropy growth and structural destruction. Biologically and technologically, civilizations in a halted expansion universe would face distinct challenges and opportunities. On the one hand, a denser, interacting cosmos might facilitate resource access, material exchange, and communication over cosmic distances, potentially supporting advanced life. On the other hand, increased radiation hazards, gravitational instabilities, and eventual contraction pose existential threats requiring extraordinary adaptability or technological mastery. Philosophically, this thought experiment confronts us with the limits of knowledge and the interplay between determinism and contingency in cosmic evolution. Can the universe's fate be altered by physical laws or even intelligent intervention? Is cosmic destiny fixed or open to change? These questions evoke reflection on our role as observers and participants in a universe whose story is still unfolding. From a scientific viewpoint, the halted expansion scenario challenges cosmologists to refine models of dark energy, gravity, and cosmic evolution. It drives experimental efforts to measure cosmic parameters with greater precision, to understand vacuum energy's nature, and to probe gravity's behavior over vast scales. It encourages exploring novel physics beyond the standard model and general relativity. Ultimately, the question, would stopping expansion save the universe or doom it faster? Resists a simple answer. It embodies the profound complexity and mystery of cosmic destiny, reminding us that our universe is not a static tableau but a dynamic, evolving narrative full of surprises and possibilities. As we gaze into the cosmos and ponder this question, we participate in a timeless human endeavor to understand the universe not only as it is but as it might be. The cosmic plot twist of halted expansion invites us to embrace uncertainty, cherish the fleeting moments of cosmic vitality, and continue the quest for knowledge and meaning amid the vastness. So, as the universe expands, or perhaps pauses and changes course, what future awaits? Is halted expansion the universe's salvation, a reprieve that prolongs life and complexity? Or is it the harbinger of collapse, a final chapter leading to cosmic silence? The answer lies hidden in the deepest laws of physics, the nature of dark energy, and the interplay of forces shaping existence. For now, the question remains open, a cosmic mystery waiting for science, philosophy, and imagination to explore. It is a challenge and an invitation to think beyond the known, to dream of futures yet to unfold, and to find our place within the universe's grand and evolving story. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.